Good. So this is the first meeting it's an EU-US virtual networking event. Some of you are already familiar with Discover Us, the project that is organizing this in collaboration with the colleagues from the European Commission. For some of you, there are some new elements here, but we will explain everything in this meeting. So you received the agenda for today. So we are started on time, more or less. So we will first do a roundtable so we can present, introduce ourselves very briefly to the other participants. And then there will be half an hour, three presentations, introductory presentations on the cooperation. So we have three talks there. One by the European Commission, and this will be done by Mr. Rolf Riemenschneider, who is also the project officer of this project. Then there will be a short recording, pre-recorded address by Jason Hallström from the National Science Foundation, and I will then finally bring the highlights of the most important information about the project Discover Us as last speaker. After that, we have a series of projects. First series of projects are European projects. We call them SWARM projects. Here you see the list. This is also the order in which we would like to present them, unless somebody has to leave early or will arrive late. So that's 6 projects. And then after that, there are 4 US projects that volunteered to do a small pitch here in this meeting. And these are the 4 probably also with the speakers that are going to present the slides. And then we hope to end all that between 5:30 and 6 o'clock. And then there will be some time for some debriefing, some this open discussion on how we see a potential collaboration. And then we hope to, well, we want to end at 6 o'clock. So that's basically it. So for the presentations, what we are proposing, so we are making a recording. That recording will be shared among us. So if you all agree that this can be shared, we will also put it in public for more people to watch it later. But it's not being streamed at this very moment. And the idea is also that you present your own slides. So normally you can share your screen. And then that means that you have full control over your own presentation. For the presentations, all the presentations are 10 minutes, including Q&A. So we would like you to respect that time and maybe talk 7-8 minutes, so there's a little bit of time for questions, and then we'll move on to the next speaker. So that brings me to the roundtable. So maybe what I can do maybe is to follow this order that is the most logical one. So maybe I will start with the representatives from the European Commission. So there are 2. Rolf.
Yeah, thanks, Colin. Thanks, everyone, for organizing the meeting. I'm head of sector for Internet of Things in the Internet of Things unit of the European Commission in the DG Connect, which is the digital part of the European Commission. And I'll talk later about our programs. And I think also my colleague Jan Komarek is in the meeting.
Yes.
Jan, are you around?
Yes, I'm here. So I'm working also in the Internet of Things unit of the European Commission of DG Connect with Rolf. And I am the backup project officer for Discover US project.
Okay. So the next one is Jason Hallström. He is from the National Science Foundation, but unfortunately he cannot be here today, but he sent us a small movie. And then there is myself, Koen de Bossere. I'm professor at Ghent University in Belgium, and I'm the coordinator of this project. So maybe then we can go to the projects. So for aerOS, there's Ignacio, I think.
Yes, it is me. Hello. Good afternoon, good morning.
So can you just in one sentence say who you are and what your role in the project is?
Yes, of course. Well, I am substituting here the actual project coordinator, which is Carlos Palau, that unfortunately couldn't be here with us, but I am the deputy coordinator for the project. We have a good track record of coordinating projects in regards to IoT, cloud computing, edge computing, and I will be here basically presenting the project and how I think we could have entry points of collaboration with the US.
Okay. And there's the INCODE project, Lina.
Yes, hello. Hello, everyone. Did you hear me?
Yes.
I had
Yes.
some connection issues. Okay. Well, hello. My name is Elena Giannakandropoulou. I work for Unisystems Luxembourg, and I am the project coordinator of the EU project INCODE. And I'm very, very happy that I'm here today.
Mm-hmm. So in case you have a colleague, so I mentioned one name, if in case you have a colleague
Yes.
in the meeting, please also give the floor to your colleague.
Yes, actually, my colleague John Avramidis is supposed to be in the call because I have a time limitation, and in case you have any kind of question, I'm sure he will be happy to respond if I'm not here.
Okay.
I don't know if John is already.
Thank you, Lina, for introducing me. I'm also part of the coordination team of INCODE and part of Unisystem Luxembourg, and I'm also very happy to participate in this event. Thank you.
Okay. And OASEES, Akis.
Hello, everyone. Happy New Year also. Best wishes. Happy to be part of this wonderful event. And I am the project coordinator of the OASEES project. Thank you.
Okay. OpenSwarm, Thomas, in the meantime, you arrived. Welcome.
Thank you so much. My name is Thomas Watena. I'm a research director here at INRIA in Paris, and I'm the project coordinator for OpenSwarm. I'm going to tell you all about it in a little bit. Super happy to be here, in particular because we have a lot of collaboration going on with the US on Swarm projects, and so I'm looking forward to understanding a little bit more about the project and how we can contribute.
Okay. So then it is SmartEdge, Philippe or Dan?
Yeah, I'm Dan here. So my name is Jan Leffer. I'm a PI from Technical University of Berlin. So I'm the technical coordinator of SmartEdge. I will be here with our colleague Filippo Cusini. He will going to present our project. Very happy to be here to learn other Swarm project in EU and the part US as well.
Thank you. Then there is Carla.
Hi. So I'm the coordinator of TaRDIS, and I'm also a professor at Nova University in Lisbon. And I have two colleagues here, Roland and Dimitra. Maybe they can introduce themselves.
Thank you, Carla. I'm Roland Kuhn. I'm founder and CTO of Actix. So I have a background in distributed and peer-to-peer systems. And over the past 8 years, I've learned a bit about factories as well.
And Dimitra.
Hello, I'm Dimitra. I'm a research scientist at Telefónica, which is a telecommunication company in Spain.
Okay, thank you. So then we can move to the US project. It's the Chameleon project. Kate, I think.
Hello, I'm Kate Cahey. I go by Kate. I'm a senior scientist at Argonne National Lab and University of Chicago. And I'm PI of a project called Chameleon, which provides bare metal reconfigurable infrastructure for computer science research, education, and emergent applications. And it's an edge-to-cloud system. So we, generally speaking, do research on cloud and edge and making strange and wonderful hardware work in strange and wonderful ways.
Okay, thank you. And there's the Eager project, Manish and Daniel, I think.
Yes, good morning and good afternoon, everybody. Manish Parashram, a faculty at the University of Utah. I work on leveraging the Continuum Edge to Cloud to HPC Continuum to enable urgent applications. Eager is a term for an exploratory project. So this is a high-risk project. And in this specific project, what we're doing, Daniel and I, are leveraging infrastructure such as Sage, which is coming up next, and other platforms to be able to support edge applications, edge plus cloud urgent applications, to develop programming support and runtime support. And I'll allow Daniel to introduce himself.
Thank you, Manish. So I'm Daniel Balwek, research scientist at SKI, but also affiliated with INRIA. And my focus is on edge to cloud application. And we have an emphasis also on urgent science, which we will discuss later in the presentation.
Okay, thank you. Then the sage, Pete.
Yes, hello, good afternoon. So I'm Pete Beckman from Northwestern University and Argonne National Laboratory, and I'm here with Nicola, who's the co-PI and deputy director of the project. And the project is to put AI out at the edge and create an entire software ecosystem and also be able to deploy it in mountaintops and across the United States. And so we'll talk about the AI and the deployments of that later today.
Okay. Maybe Nicola?
Good morning, or I guess afternoon for you. I'm Nicola Ferrier. I'm a senior computer scientist at Argonne, and I work with Pete on the SAGE project, and I actually lead the AI ML efforts on that project. And we have a bunch of different applications that run on our nodes to help address or collect various forms of data. And we'll talk about that a little later.
Oh, okay, thank you. And then there is a suite project, I think Deepu John.
Hi, good morning, good afternoon, everyone. I'm Deepu John from University College Dublin in Ireland. So the suite project is a collaborative consortium project between Ireland and the United States. We are a 3-member consortium between US, UK, and Ireland. So I'm representing our consortium here today. And the project is about distributive inferencing of AI models in the edge cloud continuum. So we'll discuss a little bit more about that later.
Yeah. Okay. So then you have seen that in the meeting there's still a number of other people. These are the partners from the project. So I'm here looking at my screen. Mark, maybe you're the first one here on my screen.
Okay, so I am Mark Duranton. I am from CEA, and we will be in this project in charge of the meeting that we will have as coordination with the US. And I am here with my colleague Selma Assayas. I think that she's also online.
She's also online, yes. Selma. You're muted, Selma.
Okay, hello everybody and happy new year. I'm Salma Aziz and I'm also part of the consortium. I'm a colleague of Mark, and we will be in charge of organizing the coordination meetings in Discover Us. Yeah.
Then I see Rosa and Maria.
Hello, I'm Rosa Badia from the Barcelona Supercomputing Center, where I lead the group on workflows for distributed computing, but this distributed computing includes also edge to cloud. So in the project, well, basically, Maria will say, but we will be coordinating the webinars, but also in the collaboration meetings, we will be coordinating the programming frameworks or programming layer in the discussions, in the research discussions. So maybe Maria, you want to say hello also?
Hello, good afternoon, good morning. I'm Maria Sancho. I'm the manager of the Education and Training Unit at Barcelona Supercomputing Center and professor at UPC. Happy to participate in the project, and as Rosa just explained, I will be helping with the webinars.
Okay, so then it's Tullio.
Hello everyone. Tullio Vadanaga, University of Padua, near Venice in Italy. Part of the Discover Us project with focus on the assignment of the collaboration grants across the ocean.
Yep. Last but not least is Ovidio.
Yes, Ovidio Vermesson from SINTEF. I'm chief scientist at SINTEF in Oslo. First of all, good afternoon and Happy New Year. I'm part of the Discover Us project as one of the work package leaders. Thank you very much.
Okay, thank you. So I think there's one more person, Philip Maximovic.
Hello, I'm a researcher at INRIA Paris, a collaborator of Thomas Watteins on the OpenSwarm project.
Okay. Did I skip anybody in the meeting here? No. So there's at this moment there's only one person missing, is Filippo Cucini, but he had told me that he was going to be a little bit later. Okay, so we are 5 minutes late, but that's fine. So the first presentation is by Rolf on the European Commission, on behalf of the European Commission. I will stop sharing my screen. So Rolf, the screen is yours.
Right. So you should be seeing my screen now. Should be coming up.
Yes. Okay,
good. So good morning, good afternoon again, and particularly for the US partners, thanks for getting up early. We are in the Commission, the unit who is behind what we call coordination and support action for supporting this activity under Horizon Europe. Horizon Europe is the main research and innovation program coordinated by the Commission, under which we have an activity on funding projects, research and innovation projects, but also innovation projects, pilot projects, and as well as this what we call coordination and support actions. I'm here with Jan. Jan is a project officer of HiPEAC, which is on preparing a roadmap computing agenda. So it's also quite relevant, and many of the partners are part of it. So what are we doing in the unit? Yes, the unit focus on Internet of Things, next generation IoT with a strong notion on industrial-driven applications. So we do not focus too much on consumer applications. We focus on industrial IoT with emphasis on what are the new technologies changing the IoT paradigm. One of the key elements, obviously, is new paradigms through edge computing, which changes the governance, but also, the way you take decisions within the IoT. In the past, IoT was driven by connectivity, connecting different objects. Later on the second stage, it was driven by services. Much of the data was transferred to the cloud. So we had many of the IoT services with cloud-based services. And we see a paradigm shift with the power to the edge, with more computing capacity at the edge. We're linked to, as said, we are supporting research innovation projects. We're looking at horizontal activities, what are the standardization issues, how to solve open interoperability, open standards, how to leverage open source. As mentioned, we are quite linked with the data strategy. The Commission is a body also doing policy and regulation. And there was under this Commission, we put a strong emphasis on a data policy, data regulation. As said, many of the IoT data went to the cloud and was leveraged at the cloud. So the data strategy looks at data platform issues, governance issues, and so on and so forth. We're also quite linked to the CHIPS Act. As said, the new paradigms introduced for new chips, new capacity at the edge. You mentioned AI embedded at the edge. So chip supply and the CHIPS Act is also a relevant policy. And then obviously we have the new industrial policy and new industrial strategy, which is pretty much around new ways of digital ecosystems and digital platforms. So this is a bit of a general view. Going in greater detail, under this framework program, we introduced the new notion from cloud to edge to IoT across the computing continuum, a strategic initiative jointly executed between the cloud unit and the IoT unit. Total investment more than 250 million euro under these 4 years. We started off with strong focus on baseline technologies, research and innovation projects, which you see in the dark blue on the top. What we have open at the moment is the light green, which is piloting activities, demonstrating piloting activities, but also highlighting the role of open source and foundational models, foundational software technologies at the edge. Also, what we supported under this recent framework is management schemes across the computing continuum. That is the greater context. And I mentioned the paradigm shift, and that is the visualization. Most of you are quite familiar with that one. So far, IoT was concerned much about interoperability issues, semantic interoperability, but also device-to-device interoperability. With the new technologies and progress made in cloud technologies, many of the cloud paradigms can be applied also to problems close to IoT, and with the new infrastructure, which actually is a game changer because it's a new type of infrastructure where you have both. You can apply cloud technologies, you can link to devices, device interaction, you can support real time, you can reduce the attack surface, increase security, you can exploit new functionality of 5G and so on and so forth. I think most of you are familiar with that one, and I don't need to go into greater detail. As mentioned, we selected under the SWARM initiative in the end of 2020, we selected 5 projects, and these were the sort of crystallization points where we see, well, you know, that could be a starting point for mutual interaction, because it's quite basic research. It's still in the beginning, not quite clear, you know, what is the path for applications. There are new programming paradigms, there are new concepts, new agent technologies combined with AI. So quite heterogeneous on one side, but on the other hand, also eventually building up a new baseline technology. And after discussion with colleagues of you, in particular with Jason, we saw there's an opportunity to build common ground here, to accelerate the research, put it on a broader baseline, and see where are the key applications in order to build on that and have a higher impact. I started to make a little sketch, you know, what we've seen in those sort of projects, and that matches quite well your introduction in the beginning. On the one hand, yes, we look at new ways of possibilities offered by communication technologies, 5G, mesh network technologies, new virtualization functions in the network. We've seen a strong push from existing technologies, cyber physical systems and digital twins, which are scaled down actually to the edge, which could be executed with downstream models on the fly and real-time environments, exploiting further agents. But we also see a couple of activities where new ways to integrate AI to take decisions supported by AI close to the IoT nodes or in a distributed manner. And last but not least, which is new or not new because it was known from the past, but still, you know, and that with the new possibilities we have is the opportunity to execute a swarm paradigms in order to tackle more complex problems. And there we don't have a clear path for application or industrial applications. There are a few ideas, and we hope that if we increase the critical mass of stakeholders and we join knowledge and we exchange knowledge, that we can accelerate that path for commercial applications and increasing the impact. One example to visualize what we mean by that is we have a hot topic at the moment in Europe about energy, reducing the dependence on Russia, tackling the energy crisis, be more resilient, moving towards renewable and advancing the decarbonization strategy for different sectors. As an impact, we see energy assets, sources popping up like mushrooms. One example is always, for instance, charging stations. So people come home at rush hours, and they come home, plug in the car, everybody starts charging at the same time. So you see that popping up. Other example would be solar panels. As soon as we have the sun shining, you know, and this could be quite a local phenomena. The sun is shining, and then you activate solar and you inject power into the grid, which definitely is sort of a swarm behavior because it starts locally and it may be modulated by clouds. So question here again, you know, what are the key algorithms, you know, to anticipate such a behavior, to mimic such a behavior? to anticipate reactions and control in the grid, avoiding that you have to have grid control in milliseconds or in seconds or in minutes, which is very cumbersome because the infrastructure is not prepared for that, and also the question how to program that. So that was one example, and for sure there are other examples which will be given today, either from manufacturing, and operating in a complex environment and dynamic environment, or another example from smart traffic, where you have this sort of dynamic behavior of cars working in reacting in with a knock-on effects, and then smart crossing. The case from logistics is quite known, that you have sort of a swarm behavior in order to solve local logistics bottleneck. Others examples are rescue services, or again the charging example, that if you're in a multi-tenant house and you have several charging stations or wall boxes, that they coordinate between each other and may react as a swarm, to needs from congestion needs from the grid, and to have a higher, quite cheap reaction demand response in the grid. Good. So that's basically all from my side. So what was our thinking behind the EU-US collaboration? So we looked at like-minded countries. We start with fundamental research, pre-competitiveness. We primarily target university and research lab, but definitely look at also at what are the key use cases to validate. The theme of concepts and distributed computing and swarm, I think, fits well what you have presented. We want to see that as a start of collaboration, and we don't want to have that a collaboration for the sake of collaboration, but we have in mind, if it works out, to have sort of a long-term collaboration in order to have also later on a strategic targeted collaboration. Good. So the question of today is basically to start identifying interesting parties, projects, coordinated from the EU on our side and coordinated by NSF from the other side. So what is the purpose of the first workshop we have in mind, online? Yeah, I think the first is, the name of the exercise today is to communicate. I think if you're in research projects in your daily work, somehow you first of all have to say, what are you doing? And then you have to think about, how could I share my knowledge and where could I incorporate input from outside, or where can I leverage knowledge from outside? So this is a fact finding. It's a bit of a process which you cannot just switch on. It takes a bit of time, and you need to communicate what we're doing and to understand the other positions. So that is the main purpose of today. We could think of coming tool, set of tools or platforms for integration. We could think of later on sharing demos, infrastructure or labs for the tool validation, or in the long term to agree or to publish a shared vision to reflecting on emerging technologies, because technology will not stop at the point when you start the project. I think there is always progress, and we have to leverage disruptive effects, or we have to look at what and how the technology landscape is emerging. Actually, that was all from my side. I'm pretty looking forward to your input today. It will be pretty interesting and exciting, and I'm looking forward to interesting and stimulating discussions. Thanks so much.
Thank you very much. I don't know, is there at this point a question for Rolf? You can raise your hand or just talk. If not, let's move on to the second presentation by the NSF and INCODE. So I just mentioned to ask 3 people to introduce themselves, which is Vicky, Maddie, and INCODE. Maybe Vicky, you should say a few words.
Hello, everybody. My name is Vicky. I work at Ghent University, and I will help Koen with the administration and the logistics of the project.
Maddie?
Hi, I'm Madeleine Gray, and I'll be responsible for communications on behalf of the University of Ghent.
Yeah. And INCODE?
Hi, good afternoon, good morning. I'm in ECHO, and I will be more on the technical side of the project, so helping different things. Yes.
Thank you. I forgot the most important people of the project because they are doing the actual work. So Enrico, you can start Jason's presentation if you want.
So do you see the?
Yes, we can see.
Jason on the screen?
Yes.
Okay. Let me know if the sound is not running.
Good morning. My name is Jason Hallstrom, and I serve as a program director with the Division of Computer and Network Systems with the U.S. National Science Foundation. I'm so sorry that I'm not able to join you in person for this exciting event and the inspiring discussions that will no doubt take place. Nonetheless, on behalf of the NSF, welcome. We are delighted to have this collection of experts present to continue shaping a new long-term collaboration among US and European researchers broadly focused on enabling seamless convergence across the computing continuum, spanning both the physical and cyber worlds. The conversations today reflect a continuation of discussions that began in 2021 as part of the Digital Around the World event, where experts from the US and the EU shared their initial ideas for new, high-impact collaborative research opportunities in computer and network systems. Those discussions continued at IoT Week in Dublin in 2022, culminating in an announcement from the NSF and the European Commission of our intent to catalyze new collaborations in this space. Some of the key ideas from those discussions are captured in a white paper included in the HiPEAC Vision 2023 technical report, which we hope will provide some fodder for your discussions today. Now, naturally, those ideas have continued to expand and evolve through ongoing discussions, including a previous workshop that was dedicated to this effort, which brought together more than 20 thought leaders from both sides of the Atlantic. We're so excited to see how this group today will continue to move the conversation forward to catalyze new joint efforts and strengthen existing collaborations between the European and American computer and network systems research communities to enable intelligent systems that operate seamlessly across the whole of the computing continuum. Now, within the U.S. National Science Foundation, the Division of Computer and Network Systems provides a natural home to support this collaboration. The division supports research and education activities that invent new computing and networking technologies and that explore new ways to make use of existing technologies. We seek to develop a better understanding of the fundamental properties of computer and network systems and to create better abstractions and tools for designing, building, analyzing, and measuring future systems. We also support the computing infrastructure required for experimental computer science, and we coordinate cross-divisional activities that foster the integration of research, education, and workforce development. Now, as this group continues to explore these ideas and to form international teams, we want to encourage you to explore the division's active investments in this space. This will not only provide some visibility into the current state of the art on the US side, it will also provide a large pool of potential research partners. That information can be found through the award search feature on the NSF's website at nsf.gov, that is nsf.gov. With that, thank you again for participating in this important conversation, and we so look forward to seeing how your ideas and expertise will shape this emerging collaboration. Thank you.
Thank you, Jason. We don't have an opportunity to ask questions, but from the interactions we got with Jason and his team, they are very eager to collaborate with us. And I will say a few more words about this when I will present here. Now, that's the next point. In a nutshell, the Discover Us project. So normally you should be able to see the screen, I hope. Yeah. Okay, so Discover Us, the project. The official title is Collaboration with NSF on Fundamental Research on New Concepts for Distributed Computing and Swarm Intelligence. So I'm the coordinator. And this is a project. So I have here some data about the project. It's a coordination and support action, which actually helps in implementing the policy by European Commission. So it started 12 days ago on the 1st of January. It will run for 30 months and the budget is €1 million. There are 5 partners, so they already have briefly presented themselves. So Ghent University, Barcelona Supercomputing Center, CEA from France, SINTEF from Norway, and University of Padova from Italy. And we also have 3 staff members that I forgot to ask them to introduce themselves. So it's Vicky, Maddie, and INCODE, and they are all working for the coordinating partner in Ghent, but they will do the actual work, organizing the calls, doing all the logistics, so that the partners can just focus on the content and not on the actual administration. This project has a very strong link with another CSA called HiPEAC, High Performance Edge and Cloud Computing, which is actually a project that supports a network that exists for almost 20 years with the same name, HiPEAC, and that gathers some like 2,500 experts in computing systems. It's more general than what we do here in Swarm Computing, but we are also using that infrastructure to support this, to help realizing this project. And the people here, the staff members, Vicky, Maddie, and Eniko, also working for HiPEAC, so this is a very good synchronization between these 2 projects. So I would like to say something about the logo. We were looking for a logo that referenced HiPEAC and also, of course, Europe and also the US. And Ineke came up with this proposal. So you have the red of the stripes of the American flag. You have the blue of HiPEAC. You have here a yellow accent on the HiPEAC, which refers to the stars in the European flag. And you also have that dot, that square here in this logo. Here you see a D in the red and you see a U, Discover Us. We call it Discover Us because we are inviting the American colleagues to discover us here in Europe. But at the same time, we are also encouraging the European partners to discover the US or the USA, United States. So it has a double meaning, and we strongly believe that this is going to help us in order to make this project a success. The goals of the project, this is actually mostly taken from the call text because we have submitted this project in the context of a call. So it was to strengthen the long-term collaboration between the EU and the US, as already mentioned by Rolf. So we are looking at strengthening the strategic alliances and also to foster long-term collaborations between research. It's pre-competitive, it's mostly between research institutions and universities on both sides. We also want to promote, organize, and facilitate brokerage events. If you want to collaborate, you have to know each other. So that will be networking events, summer schools, this kind of things. We will implement a research exchange and fellowship program. So we have set aside a budget for about 20 exchanges of 1 month, going from the European Union in the direction of the US, the United States. And we have a commitment from NSF that they are going to match these funds, so also to allow to fund 20 exchanges between of US research coming to Europe. So that's about the scale of this project. So that's like 40 exchanges, 50% in the direction of the US and 50% in the other direction. And also this project is also going to support the collaboration infrastructure by organizing networking events, doing the dissemination, promotion of this project and so on. So this is, we're going to work for both sides here. So we want to strengthen, promote, implement, and support. So what we are going to do, measures, the coordination and support measures that we propose are vision building. So we will organize a number of common initiatives and also workshops and work on a vision for this project. So I think bring the research together during several days, brainstorm, and the result will be a white paper with some, ideas from swarm intelligence, distributed computing, the computing continuum, and so on. So there will also be networking, and the idea is to bring projects from both sides together, to have different tasks and different projects working together and meeting each other, just visiting each other and collaborate physically in a place. So then the research collaboration is the instrument that we are going to use to support this, to fund this. So we will add some money to that. And then there is also the community management, communications, dissemination, etc., which is done on top of that. So you have the vision building stream, you have the networking, research collaboration, and the community management. And the research areas we want to be active in are listed here. So there's cross-cutting over all the activities that we are going to do. So we want to look into ways to manage complexity through high levels of abstraction. We are looking for new concepts of distributed computing and swarm intelligence and edge intelligent things. We are looking for AI-based concepts for self-organized, dynamic, and adaptive management. And also we are looking for collaborative programming frameworks and software development tools. This is the tools part of the project. So this is in a nutshell how the project is structured. In the proposal, we sometimes talk about CCDCSI, which is hard to pronounce, but this is about the computing continuum, which will be an important keyword, distributed computing and swarm intelligence. So this is then translated into 4 work packages, 3 technical ones and a management one you can see here. And just to give you an idea of the activities, tasks that we have. So for the cooperative networking, we are going to organize networking events, 1 networking event every 6 months. One of them will probably be co-located with the HiPEAC conference, which traditionally takes place in January, and there will be another one in the summer, an event where we will try to meet, to bring people together, organize activities. There will also be a summer school, which will normally take place in December, obviously in July. That will be in collaboration with the HiPEAC Summer School. And that's for the physical events, in-person events. We will also have virtual events, and these are the webinars. We will have monthly webinars where American and European researchers will sometimes do a webinar together, or maybe do a webinar on one of the projects they are involved in. So, but that will also be a way to grow a community, people that feel they belong to a community, to discover us a community. So this cooperative networking will then lead to a vision development. And there are 2 aspects here. There are the vision workshop, which will be a kind of, we call it a kind of Dagstuhl type event. So most of us here in the meeting know what Dagstuhl means. So we will meet during several days and really brainstorm on aspects, and the aspects have already been mentioned. So that's the abstractions, the new concepts, the AI-based support or techniques that we can use, and also the programming frameworks and tools. So this is planned in June of this year already, because we have to think before doing actual work. And then there will also be coordination meetings between the European Commission, the unit where Rolf and Jan belong to, their partners or the people at the NSF doing similar work, and also the project coordination. So that's for the vision development. And then there will be exchanges. So we will organize calls and do the evaluation. This will happen in Europe, but it also will also happen in the US. And then, of course, we will do the actual exchanges. And there might be some communication and dissemination of the results of such exchanges after the exchange took place. And then for the management, there is the community building. So we aim for something like 35 to 50 researchers in Europe and a similar number in the US. That means that we will have a community, a transatlantic community of around 70 to 100 people. And these are the people who are going to think about the white paper, so the vision workshop that we are going to organize. And they will also be the major beneficiaries of the calls and the exchanges. So that's the idea, that we have some kind of group of people that we know who are willing to collaborate, and then we will try to work with these in this project. And of course, we will also do the proper communication and dissemination of the results of this project. So that's basically in a nutshell how the project is going to work. Maybe a small timeline for the first year. So here you have the different work packages. So maybe a number of important things is community building. So here we want to create that community between 70 and 100 people. So this should be in place by April, May. And then we plan to organize a vision workshop in June. So that's an important one, because this is going to lead to a white paper at the end of the year. And it will also lead to a call here, the first call open one and call close one. So that will be the time, 3 months that the call will be open for the first exchanges. In parallel, there will be here the webinars, and there will be the networking events, the summer school, so all these things, and the coordination meetings between the NSF and the EU. So that's all running continuously. And in the second year, there will be 2 more calls, and there will also be an update of the white paper at the very end of the year, the last 6 months. So that's basically, in a nutshell, what this project is all about. And this meeting is actually the first meeting to bring a number of projects together and to see whether there is an interest to join this project, as we call them members. That could be an outcome of this project, and then start working. So we have some internal communication channels that we can use in order to share information and to start collaborating. So that's it from my side. Other questions? By somebody?
So
Thomas?
Yes, I may have a very naive question. So are we talking about coordination and between the different projects that we'll present today, or are we talking about the wider EU and US communities?
Well, what we would like to have is that there are projects on both sides. So there must be some kind of project involved. And the idea was also, as we are thinking now, that it's not a PhD student that wants to go to the US for 1 or 2 months to just, in the context of a PhD. It's more like principal investigators that visit each other for 1 month to work together. So that's what the model that we have in mind. It doesn't mean that we cannot change this, but that at this moment, this is the kind of model we have in mind, yes. But it's definitely not limited to the people in this meeting today, because this is just a choice that we made. And also we are looking for between 70 and 100. So that's many more than we have today in the meeting.
Very clear. Thank you so much.
Yeah. More questions?
Yeah, I would have.
Yes,
I would
that's
have
you.
one. Yep. Is this information somehow available anywhere, or as you just barely started, is the first time you are making this public, I guess?
Well, I can also answer that question. The kickoff meeting, the actual kickoff meeting, will take place next week,
Okay.
Where we will have more. After that meeting, we will have more details on how we are going to organize things. So we have a kickoff meeting on, I think, Tuesday, and on Thursday there's a public kickoff meeting at the HiPEAC conference, which is taking place next week. And so there will be public announcements, and from then on, you will find much more information at the website. If your question was about this meeting, we will collect all the slides. We already have most of them, by the way, and share them between the people attending this meeting.
No, my question was more for the details on, how you're planning to organize all these, for instance, the exchanges, who can apply for how long, etc. All those details and nuances, I guess they will be online later when you
Yes, they will be online,
IPEAC, etc.
Yes.
Yeah, basically.
But it will be the Discover Us website, because it's a different project. So the best way to stay updated is that you apply for membership of Discover Us, and then you will get regular mails and information on new calls and activities that we're organizing, events that you can, the webinars that we will organize on a monthly basis. So
Okay.
the best way to stay in touch is to apply for membership of this project.
Apply of membership is already available, and the details for doing that are also.
We will announce this after the public the public kickoff next week.
All clear, Cohen. Thanks.
Yeah. No more questions. We have time for questions at the end. Okay, so this means that this part of the agenda is over, and that we can now move. I think you can see this, to the European Swarm projects, and for that I have a different chair. Ovidio, you are going to chair the presentations of the projects.
Thanks, Cohen.
Yeah.
And thanks to all the presenters. Do you hear me?
Yes, we can hear you.
Yes. So thanks to all the presenters that are present, and we would like to follow the presentation as is presented in the agenda, and kindly ask the speakers to have a presentation of around 7-8 minutes and keep up to 2 minutes for questions and discussions. So in order to start, I will invite Ignacio to present the aerOS and describe the achievements and the main points in the project.
Yes, can you hear me well?
Yes, and
Great. So
you can
let
share
me see
your presentation.
if I can share the screen properly, and you let me know if that's indeed the case. Can you see the screen?
Yes, we can see it.
Yes, yes.
Okay, that's great. So thank you, everybody. I will try to be very brief because Cohen instructed us to keep in 7-8 minutes, so I will try to stick to the time. I'm here representing the aerOS project, one of the 6 projects that were funded under the Data 0105 2021 call, promoted and funded by the European Commission, the unit that Rolf, Max, and Jan are coordinating. So this is where I come from. I am representing the project coordinator here. aerOS is a project focused on or coming from the origins of moving the data explosion that we are all witnessing for computing into the cloud computing sites to, well, closer to IoT sources, right? We ourselves come from the realm of IoT, so we're experiencing in low resource hardware, in the different drawbacks and pitfalls that were there, how we overcome that with different integration and interoperability technologies. And we believe this was the moment to make the joint between the cloud and the edge. That's where this project came from. Our idea was, although there are several technologies present that propose and allow for edge computing, and for edge computing, mobile, MEC, cloudlets, there is a wide variety of those deployments and standards and underlying computing hardware, and we embodied the challenge of trying to seamlessly integrating at least a part of the most relevant part of this variety into a homogeneously continuum meta operating system for this continuum. This is what we are trying to do, focus mostly on these 4 areas: cloud centricity and cost, moving these advantages that were included by the advent of cloud native technologies, moving them into the edge side. Also focus on network management and all around virtualization and security and trust. Having that in mind, we propose to design and build and virtualize platform agnostic meta operating system, right? With a clear architecture, coming from the bottom in the hardware with an operating system, and elaborating on our own blocks based on open source technologies that would allow to use the context awareness, the support intelligence, supporting the scalable data autonomy, having in mind clearly all the different EU regulations and EU principles that Rolf mentioned at the beginning, to coming from a unified single window software that helps abstracting the underlying complexity. With technology we are proposing, it's being validated in 5 use cases in relevant sectors that we consider key for Europe, but also US, like manufacturing, renewable energy, this is very crucial right now, machinery, logistics in maritime ports, and more locally in smart buildings. We are bringing relevant European actors trying to have this making reality, right? In that regard, we propose open source architecture that is transformed in turn into a set of modular technologies that conform what we call domains that group different computing continuum nodes that can embody a wide variety ranging from IoT devices to far edge computing elements to edge cloud elements that can compute some load, that allow the federation of those computing, applying certain services, network, and data. So we have these 3 main blocks that can be integrated in these domains, and we are creating certain federation mechanisms to make this connected. Just for you to just pop into your mind some of the technologies we are using, we are both creating custom software and also integrating open software that is provided in the state of the art, like the ones you can see there, coming from the idea of moving cloud native innovations into more terrain of the edge and low resource equipment with technologies like QEdge, NGS ILD, FiWare, which are European official endorsed technologies, PowerTop, Cilium IoT, OpenAPI, GOPF, and others. In that regard, we believe that we might, in the next few months and years coming, thanks to the Discover Us presentation that Cohen made, and also from some ideas we have, establish a long-term collaborations, starting from, of course, Discover Us, but also, for instance, we are launching now in the project a series of cascade funding to financial support to third parties. Now, I must say this does not allow US funding exactly, but if you have some counterparts or collaboration, you could apply with those entities, or we try to publish our software open source. We have some public repositories that you consult. There are also some sideline initiatives like the Next Generation Internet coming from other units that has sometimes open calls that can make us collaborate together. And of course, for new initiatives in the future, new proposals in which we could be together or participating into, for instance, standardization working groups working together with these continuum technologies. I must say that I have heard some very relevant things from Chameleon, Sage, and the other projects that resonate very much with our very own goals. So I am very happy if we could establish some connections there. This is the whole panorama of the partners that are part of our project, and I will be here very happy to share more information with you at any time. Thank you, and that was all.
Thank you very much, Ignacio. Very nice presentation. So now we have time for a few questions from the audience. So Ignacio, maybe I can start just to warm up the audience. What do you consider as the elements developed in your project that can be seen as beyond the state of the art that we have on the development?
Yeah, well, there are many, but the first and foremost would be that we are trying to achieve the goal of orchestrating a workload in our environment where the infrastructure is heterogeneous, regarding the container deployment frameworks. So we are trying to be able to let the user deploy a workload independently of if underlying there is a Kubernetes clusters or multi-clusters of Kubernetes or virtual machines with some other kind of container deployment frameworks. We are trying to make this transparent to the user and also let the system smartly learning from the previous assignments of where their workload was most optimal in its allocation, and try to do this within the very same system. This for starters. We are also investigating a lot on the data composition and the federation so that data can be accessed from several points of the continuum without compromising security and privacy of the exchange. I would clearly highlight these 2 points.
Thank you very much. So other questions or comments?
I don't see any. I just say I am available and just willing and looking forward to collaborating with you. Thanks to Discover Us.
Okay, thank you very much, Ignacio. So then let's move to the next presentation from Lina, INCODE. So Lina, the floor is yours.
Hello, do you see me and do you hear me?
Yes.
Great, great. Give me a moment to share my screen. Do you see my screen?
Yes, we can see it.
Okay.
Maybe you can put it in, yes.
Like this?
Mode. Yes, perfect.
Great, great. Thank you very much. So once again, I would like to say hello to everyone. And before starting, I would like also to say thank you to the coordinators for organizing this really insightful event, especially for possible collaborations with other projects. As I said before, my name is Nagiana Kandropoulou. I'm the project coordinator of INCODE. and that I'm about to present you. So I will start the presentation starting with what do we mean when we say IoT edge to cloud. In very simple terms, we refer to a combination of sensors, mobiles, and other computing devices that are connected to each other and to the cloud through various communication channels. I think there is a big challenge there, as these devices are quite diverse in terms of communication protocols, hardware and software. So the question is, how at the very end can we exploit IoT processing capabilities, and how can we enable intelligent collaborative deployments? And this is where INCODE comes into play, since INCODE is trying to build an open continuum framework with continuous infrastructure and service layer programmability, while at the same time, in the INCODE project, we are trying to ensure secure operations with all these edge devices, since they typically operate in sensitive environments. So what INCODE does, what are the innovative areas that it brings? First of all, INCODE uses a resource management layer that runs across the entire ecosystem, and it offers microservices like infrastructure manager controllers, drivers, core components, and security services. And also, it has an end-to-end service management layer, allowing applications to run on the underlying hardware and offering services like role-based access control, runtime orchestration, telemetry, software lifecycle, among others. So what I showed you in the previous slide is what are the components that constitute INCODE framework. In this slide, I know it seems a bit difficult to understand, but I just want you to show to you how these components that I mentioned before, the resource management layer, the blue one, the service management layer, the purple one, and the service package, if I can name it that way, that runs vertically with the other two layers, are interconnected. And beyond this, I want to show you how this platform, the INCODE platform, can stand upon any physical layer infrastructure, spanning across IoT sensors, core infrastructures, or communication protocols. So my point today is not to make a technical presentation. My goal is to give the main idea and how INCODE works. So allow me to pass to the application areas in order to get more understandable. And I will start with our first application area, the first pilot that we have, dealing with the dynamic world of logistics. And what INCODE does, INCODE introduces a transformative solution in order to optimize transport of the goods, and at the same time, it tries to optimize inventory management. So I will try to explain you the figure. Imagine that we have a fleet of trucks that can dynamically share real-time data regarding good transport conditions. Now picture that this data can seamlessly flow to our local edge node at the warehouse, where they are authenticated in real time. And at the same time, we have IoT sensors at the warehouse, static sensors in workers, in forklifts, that contribute at the inventory status information. So INCODE is trying to merge the local data and the cloud intelligence. And the result from this is that we have at the local edge node that receives commands in order to manage a swarm of end devices and vehicles for loading and unloading of the trucks according to ad hoc needs. So the benefit that we have from all this is that we can have optimization of the loading scheduling, which can prevent damage of the goods, reduce unit costs, and of course increase profits for all logistic stakeholders with our coordinated loading and unloading system, prioritizing work safety, and of course prevent any product mishandling. And now let's pass to another application area. Let me pass to this pilot, application area 3, which now this time in the manufacturing domain. And what INCODE tries to do here is to, while using new technologies, is trying to incorporate IoT sensors, collaborative robots, wearables, exoskeletons, in order to create a smart worker assistance. Systems, I'm sorry. So once again, I will try to explain how this smart factory will work. Imagine that we have workers, operators using IoT sensors, let's say wearables this time. These wearables will produce high resolution data that will be recorded and will be pre-processed somehow. This data will be sent to an edge node in order to have advanced processing and in order to generate and visualize stress indicators. These stress indicators will activate somehow some intelligent actions, and these intelligent actions can lead to rescheduling of the factory pace. For example, if the stress indicators will be high enough, we will expect that the pace line will slow down. We will have the pace, yes, will slow down till the operator parameters will return to the usual state, or until the operator will be replaced. So what we have a system that responds to the well-being of the operators by using vital signs in order to trigger the baseline of the factory. And of course, all of this is by optimizing that way workers' position. So what we have gained, of course, safer working environment, improved labor efficiency, and of course, better informed workers. And last but not least, we enhance that way maintenance and fault detection times. So the impact that INCODE believes that will bring in technological side, we can talk about easy interconnection of multiple IoT platforms, creation and management of applications in industrial environments, but always in a reliable way. And from a business perspective, as we also saw in our pilots, we could say that we promote new business opportunities, not only for stakeholders that exist already in the continuum, but also for new industries. And this is our team. And thank you for your attention. I would love to hear your questions.
Thanks, Lina, for your presentation. So we have time for 2 questions. So you are invited to ask or comment on the presentation that Lina had.
This is
Roland, please.
Lina, you said you can use any physical layer. I guess that has some properties. Which examples are you using in the concrete use cases that you use to demonstrate it?
You mean for the use cases that I showed you as a physical layer, like IoT sensors or okay, for example, in the smart factory we use wearables or exoskeletons or robots, and
I meant the network layer. Which kind of network?
If I'm not mistaken, in logistics, in the application area 1 that I showed you with the logistics, we use ultra wideband, and I think 5G as well. 5G as well. And for the application area 3 with the smart factory, we once again open radio access network and 5G.
Awesome. I would like to talk to you later about ultra wideband.
I would love to.
No.
Most probably I will not be here, but my colleague, I'm sure, in order to exchange a lot of ideas.
Yeah, thanks.
Thank you.
Thank you very much. We have time for 1 more question, if you have. Maybe I will ask 1 question very shortly, related to scalability of your solution, because we noticed that you offer a platform that covers the whole continuum. So how this platform addresses scalability, starting from very simple devices to more complex devices?
Scalability, you mean? Do you want you to? I'm not sure that I understand.
Scalability of the agents that you deploy on your physical devices, because you have different devices in this continuum, some with very restrained resources, memory and processing capability, and other much more complex.
You mean how we're trying to integrate all these different devices?
How you address this, how you solve this?
Well, I think the integration of all these different devices with different protocols, with different restrictions, I think as a preliminary stage, we use open source components for this kind of challenge at the moment. For example, we use as orchestration tool Kubernetes in order to find a common way a common toolbox to speak with all these devices, at least as a preliminary state, of course. I don't know if I have answered your question or.
Yes, it's perfect. Okay. Thank you very much, Lina.
You're welcome.
So then we move to the next presentation, Thomas, OpenSwarm. So the floor is yours.
Thank you so much for giving me the floor. Let me just start the presentation. All right. So my name is Thomas Watene. I'm here at INRIA, coordinating and serve as a coordinator for the project. Let me just move this 1 second. Yes. So this is you can see the partners that we have here on the left-hand side. So this is a project between INRIA, Analog Devices, IMEC, Ingeniarius KU Leuven, Siemens, University of Sheffield, and Falco. And the ambition of the project is to trigger the next revolution, truly collaborative smart nodes. Sorry, let me go back there. Device augmented with embedded intelligence to interpret and understand the data they're generating, communicate efficiently, even when moving around. So you see here at the bottom our consortium during our kickoff meeting in January last year. And then you can see here the 3 scientific pillars. The first one is orchestration of collaborative smart nodes. That means communication between different moving devices. Think of little robots. security, how do they communicate security, and then how do they coordinate in a decentralized fashion. The second pillar is collaborative edge-aware AI. So there's cool, as you may know, there's cool new AI-capable low-power wireless microcontrollers that are on the market, and so the question is, how can you use them to coordinate our different devices, and how can we, deal with the fact that there are central nodes, there's devices, and how can we do AI across that continuum? And then the third pillar is swarm programming. So, having a large swarm of these devices, how can we program them in a manner that's a bit more efficient and intelligent than just individually remote controlling each element? And then how can we enable, no operator to express what he or she wants and going towards a swarm compiler? So in practice, we are exploring those three scientific pillars, and then we're running this on test beds. So we have 2 test beds. One is a 1,000 dotbot test bed. So you can see these dotbots there. These are these little car-looking things. And we're building 1,000 of them that will be running around in Limerick in Ireland. And then we have in Sheffield this table here with 1,000 devices that we call kilobots. Also, on those 2 test beds, we'll be able to test and run all of the software that we're developing. And then after that, we are implementing those ideas and testing those ideas in 5 real-world use cases. 1 on cities and communities, 1 on environmental monitoring, another 1 on environmental monitoring, POC 4 on industrial applications, and POC 5 on mobility. Just because of the interest of this group, let me focus on 2 of them, which I think are the 2 more relevant cases for our discussion here on swarms. POC 2 is an environmental monitoring, and the idea is to support human workers in harvesting wild food. I'm sure we'll be sharing the slides, so I'm sure you can read the text, but in reality, in a nutshell, what this means is that you have people that are harvesting, that are walking around forests and picking wild fruit. Can you help them with a swarm of drones? We have drones flying above the area with cameras picking up where the fruit is, and then telling the people on the ground, you should go to that tree rather than that tree because there's many more fruit in that tree. So in a nutshell, that's what we're doing in POC 2. And then in POC 4, this is a industrial application. So imagine a factory where you have AGVs, little automated cars driving around and human workers moving around, and then machinery. Equip all of these with devices and have those devices constantly monitor how far they're from one another and essentially warn the workers when there is a possibility of a collision and halt the AGVs when they're in close proximity of a human worker. So these are the, in a very quick nutshell, what we're doing in OpenSwarm. One thing that I'd like to mention is that I think it was Rolf, you mentioned the term vision workshop. We actually have been collaborating quite a bit with the US through this project already, and we organized what I believe is the equivalent of a vision workshop in September last year at INRIA here, where you can see those 26 people and the 12 entities that are meeting, European and US partners, around the concepts of swarms, crystal-free radios, and chip-scale wireless systems, with the ambition to identify a common research and innovation roadmap, which I believe is maybe related to the concept of a vision workshop. So excited to be participating here and looking forward to answering questions. Thank you.
Thank you very much, Thomas. So again, time for 2 or 3 questions.
I have a question, Thomas. Is there a document, an outcome of this workshop?
We're working on it. Not yet. Not yet.
Okay.
It's on my to-do list to finalize this document. It will become a publication. Yes.
Okay. Good.
But I'll share it for sure.
Okay. Thank you.
Hi, Thomas. This is Deepu. I have a quick question. You said there is some test bed in Limerick, Ireland, but I could not see any Irish partner in the project. So is it?
Yes, I was hoping you would react to that, knowing where you're sitting. Analog Devices. Analog Devices is the partner in Limerick, Ireland. They have a large building called the Catalyst that you may have heard of. which is a very large, essentially warehouse, and they're setting aside a whole lot of square meters for this test bed to be, or these little robots running around. So if you drive past in the next couple of months, you should see lots of LEDs driving around.
Thank you.
In Limerick, yeah.
Other questions, Thomas?
Yes, Thomas, can you give us very short ideas of how are you progressing on this programmability pillar, the pillar 3?
Pillar 3. Yeah. So this is work led by Professor Roderick Gross from the University of Sheffield. The idea is to, these are big words, but the idea is to install a virtual machine on each of the swarm elements, on each of the agents, and then have a operator interact with something that looks like Scratch, for the lack of a better word. You have a website on your local computer, you put some blocks together, you press on a button, it creates a bytecode that is then distributed over the wireless network into the different devices, and there's a virtual machine that interprets that bytecode. And so we're defining the primitives. We're looking at fundamental primitives for robotics, go to a point, follow one another, these kind of things, but also related to sensing, find the highest point on a certain gradient, those kinds of different ways of describing what the operator expects from the swarm to be doing in an expedition.
Thank you. Do you have any paper or any document that you can share on this? Or?
We do, yeah, for sure. I
Okay.
can share. If you can send me just a very quick one-line email, I'll just respond with the documents I have, and I can put you in contact with a person. Thank you.
Thank you.
Thank you very much, Thomas. So then we move to the next presentation from OASEES. Akis, please, you can share your presentation.
Thank you. You can see my screen, or
perfect.
Perfect. Okay, great. So greetings everyone, happy to be here. I'm a project coordinator of the EU project OASEES. I'm a research associate in the National Center of Scientific Research Demokritos, the largest research center in Greece, located in Athens. OASEES has just become 1 year old this month. It's a 3-year project with an approximate budget of 8 million. We are a quite large team of around 21 partners from 9 European countries. And we are also the coordinator, along with IMEC, which leads the technical management staff. Our main objectives of OASEES is to, first of all, design and introduce the decentralized autonomous organization paradigm, which is a blockchain-based technology, into the swarm intelligence concept. And along with that, to protect and fortify native device support and privacy through the self-sovereign identity paradigm, which can help us further support persistence, global resolvability, and cryptographic variability along different devices. And through the more application layer stuff, we are also building the so-called rapid development kits, which are basically customized software development kits for the different devices, since we support a set of different vehicles, a set of 6 different vertical use cases. I'm going to shortly present 2 of them in the next couple of slides. And of course, we fostered the creation of an open source community, first of all through our the SDK that we're building for the different devices, but also for the different development kits. One namely is a quantum development kit developed by Focus, which is the CRISP, which has also been recently been added as an Eclipse Foundation project. This is a general overview of what we try to build and achieve through OASEES for swarm intelligent swarm architectures. A good, let's say, narrative can go from a top-down approach where we are currently use as the core element of programming in swarms a unified development notebook. And from there, we are split among different layers, from the programmability layer to the swarm organization layer, where also the DAOA DAOs paradigm is inserting along with the SSIs. And of course, the deployment and execution layer at the edge, where we also support the implementation and integration of different cloud accelerators, as we call them, whereas these can be from quantum-powered machine learning QNNs to one of the most recent ones, spiking neural networks, which is energy-efficient neuromorphic computing design. Our use cases come from the e-health to smart buildings to EVs to wind turbines and drone operations. And if we could, let's say, summarize and have a step-to-step guide, it would be of what we are trying to build is that we want to build something that can support any type of sensor devices, at least what we're trying to achieve, and by involving many different and divergent use cases. This can implement and support and bring on board the different decentralized identifiers and verifiable credentials, create each of their own DAO and organize through it. And through that, they can be able to choose and define their AI optimization model, use the preferred AI accelerator, and then proceed with an automated decision-making, but also human in the loop, in order to at last optimize and collect the different KPIs. The main aspect of the DAO is that it is a paradigm that we try to integrate to have the decision-making both from the sensors, but also from, let's say, human specialists in some sense, where one device or one specialist can create a proposal and then the devices can automatically vote upon it. So this is an already working blockchain-based technology, the DAO. And we try to introduce and integrate it in a swarm environment. One of the use cases that we use is develop is the electric vehicles fleet and grid optimization using edge and swarm intelligence. What is the case for this use case is that an electric vehicle fleet operator with a respective drivers community wants to optimize the recharging schedule to address local technical requirements from a grid operator in presence of local congestion or maintenance of the grid. So through collecting different types of data from the EV fleet operator, from the drivers, from the grid operator, but also the charging point operator, we build an automated interaction and coordination of smart contracts expressing individual EV drivers' preferences on daily routes and charging times through blockchain and decentralized marketplace. So what we want to achieve is to optimize or at least make a game theory-like scenario where we can optimize the charging routes for different car vehicles, but also maximize the profit of a grid operator, but also the charging point operator through decentralized marketplace. And the second use case that we were developing is involved on autonomous drone inspections. And we operate a drone swarm in a self-organized based manner in order to showcase also converged connectivity for 5G drone communication, but also dynamic governance for drone operations over distributed ledgers. This combined also with different accelerators. The first one is the previously mentioned quantum-based operations for route optimization for the drones, and also the second one is referring to spiking neural networks for object detection. I want to demonstrate these novel edge acceleration technologies and also demonstrate energy consumption through spiking neural networks, and also how quantum programming can also be integrated in a swarm relevant and edge environment. And some key points that we see we could further collaborate with our respective US projects is what we are building. Of course, most of our parts are also open source, but we could partner with a US-based project that would also focus or are interested in the notion of DAOs to enhance edge computing governance models, to exchange also insights on decentralized network management for swarm intelligence systems. Of course, our stack, which is about to release its first version release, could also be shared and validating and helping support to validate this toolkit across other US-centric use case for broader applicability. And of course, we could also jointly host hackathons and innovation challenges to stimulate development and adoption. And I think this concludes my presentation. So thank you very much.
Thanks, Takis. So time for two short questions.
I have one. I'm interested on understanding how are you programming, or which paradigm or libraries you're using for the quantum devices.
The quantum device is based on the framework QRISP, which is a framework developed by Focus, which is a Python based. And what they have achieved is that without the need of knowledge of qubits, of how qubit-based programming can be, just with the knowledge of some Python, you can create programs, simulate in a simulated environment, but also with some hooks on real quantum processing units. You can create and run some quantum-based programmings. The one we mostly use is the TSP, the traveling salesman problem, which we apply in our use case. But I can also share in the chat the link for the project that is involved in the quantum development.
That would be great. Thank you.
Thank you very much. Other questions? So if not, thank you very much, Akis, for your presentation. So you will share the slides and you will share as well the link with the partners. Okay. Yes, let's move to Carla.
Okay.
The presentation from TaRDIS.
Yes.
And then we come back to Filippo when he solves his problem.
So I don't know if you can see my screen.
Yes, perfect.
So I'm, as you said, Carla, I'm the project coordinator of TaRDIS. And this project has 11 partners. They are here presented in this slide. And the concern we address in this project is the fact that building swarm applications is highly complex and requires expertise. And having these teams with the expert developers is not available for SMEs. So we wanted, our goal, as we state here in the slide, is to significantly ease the complexity and reduce the effort of building correct and efficient heterogeneous swarms. And what is our approach? So this is a very complex image, but I'll explain it bit by bit. So at the core, we are proposing an event programming model. And we selected this event programming model because it brings you some features that are relevant here. So like features like abstraction and compositionality. And this is very important because you want to reason about these systems. So we need compositionality so that verification techniques we want to apply to these systems can scale. And so this is one of the, I would say, the main advantages of our approach is that we propose to give some correctness properties. Of course, you cannot prove full correctness on real systems, but we will prove some properties of these systems. And we have high expertise on this topic. Moreover, to make this task of building these applications easier, we provide distribution, data management, and machine learning APIs that provide to the user very simple programming abstractions and hide underneath the hood all the complexity of these decentralized protocols. Moreover, this TaRDIS development environment that I was showing you here is then supported by a runtime environment. And here we want to support heterogeneous devices and different runtime environments. So in practice, we don't want to build everything from scratch. We are already using systems and tools that are already available, and we want this environment to be open and to not just our protocols and implementations, but to other existing open source systems and tools. I have here some examples, peer-to-peer, Kafka, there's just some examples. So that is our approach. And we applied, as I didn't say that in the beginning, but we want to validate all this approach in 4 use cases. And next, Roland, actually Dimitra, is going to present one of our use cases.
So Telefónica's use case revolves around intelligent homes, where a range of highly heterogeneous devices work together with artificial intelligence algorithms. So, for example, in this picture, normally such devices learn neural networks through federated learning that is coordinated by a developer interface and third-party services. The main concerns of this scenario are the privacy of personal information, especially given the heterogeneity of computational resources. In particular, some devices might not be able to train locally a large neural network. Our goal is to exploit the hierarchies that may naturally arise in the system to develop a privacy-preserving federated learning and allow resource-constrained devices to participate in this learning. So, for example, through split learning. An example of the hierarchies might be the close-by beyond 5G base stations or a more powerful device. TaRDIS, the toolkit that TaRDIS will develop will help us to abstract the infrastructure, data distribution, and learning algorithms from the developer in order to achieve collaborative intelligence, irrespectively of the heterogeneity in the system, and a correct by design development environment for privacy-preserving solutions. That is for Telefónica.
So next we have Roland. Oh, sorry, too fast. Roland.
Yeah, thanks. So the ACTIX use case is implemented together with one of our customers, which is a German machine building company. A modern factory wants to be both agile, which means being able to introduce new products, the capability to produce new products quickly, as well as flexible, which is the capability to switch the production from one product to another very quickly, down to lot size 1. Now, being able to orchestrate this, being able to run the processes that make this possible, first requires transparency across the shop floor. You need to see what's going on. You need to understand how your factory works in order to get ideas on how to optimize it and so on. And then you will want to steer it. You will want to control it. And all of this requires digital means for reading and writing to the processes on the shop floor. Now, anything digital on the shop floor in past factories has been done using so-called OT, operational technology, which is real-time PLCs and so on, which are extremely inflexible and expensive to adapt. So this is not sufficient. We need to go to high-level languages so that we can efficiently describe the part that is not how the motor moves the robot, but what the robot does. This is the collaboration between these parties in the factory, which is a very collaborative environment. Now, this introduces IT on the shop floor, and doing so needs to be done carefully. In order to avoid friction when rolling things out, we don't want to have unnecessary touch points, which is why we designed our system to only require Wi-Fi to be provisioned so that the devices can talk to each other. But also, this is required for maximum resilience because previously people used paper and that just always works, and IT doesn't have the same quality if you use a central service. So this means that we switch to a peer-to-peer swarm-based approach, which brings in lots of problems because a swarm environment is notoriously hard to program. It's very chaotic. All sorts of things can happen. And that makes it very challenging. And as Carla initially said, the goal is to make this tractable, to provide tools so that you can graphically design protocols, verify that they make sense, and then also ensure that the code faithfully implements them. Thank you.
So I'm currently, so I have here an overview of the research collaborations we have currently in the project. We are interacting with protocol labs and integrating with their protocol peer-to-peer. And Zero also, we are starting a collaboration. And I put it here, a company that's outside of this scope, so it's OutSystems. And this is a low-code company, but in fact, OutSystems, the collaboration we have with them, it was very important in bringing inspiration to this project. So their low-code approach was a kind of the theme we used when we were writing the proposal. Of course, we have loads of collaborations with other academic institutions in the UK, but not so much with the US, and we would like to expand these collaborations obviously. Thank you. That's all.
Thank you very much to all of you, Carla, Dimitra, and Roland. Now for the audience, do you have questions to the presenters of TARDIS project? So it's Friday afternoon for Europe and Friday morning for US, so maybe the activity level is not at the highest point.
Increasing by different reasons, right?
So
Peter,
well,
please.
Go ahead. I have a question. We're in the middle of a big snowstorm here, so this is my backyard. So I'll have to go outside and shovel at some point this afternoon.
So with respect to the swarm, we're really interested in that as well, the communications. Are there any toolkits that you've already started with that you're exploring, things that are already available as an open source starting point?
Yes, we have already some toolkits that we could pinpoint you and send you. There are implementations, open source, and there are papers that we can give you. So for the communication, here the distribution API already have quite developed solutions. So I can send you information. If you send me an email, I'll reply with more information.
Okay, thank you, thank you.
And by the way, Peter, we can share some experience on shoveling the snow at minus 20 degrees from Norway. So we can send you some images. Okay, thanks a lot. Let's move to the presentations from US SWARM project. So we have Katarina, the one that is the first on the list for Aragon National Laboratory on Chameleon.
Okay. Can everybody hear me?
Yes.
Yes.
Yeah?
Yes.
Okay. Fantastic. Let me share the screen here. Okay. Can everybody see the screen?
All good.
Yeah, we're good to go. All right, fantastic. So Chameleon is an experimental testbed for computer science research. So that means that we try to support, so it's an edge to cloud testbed. So I'm going to be talking both about edge resources and resources in the cloud as well. And it started as a cloud testbed that was based primarily in the data centers, with 2 data centers, one at University of Chicago, the other one at Texas Advanced Computing Center. I'm the PI of the project, and I'm at University of Chicago. So we support very diverse range of hardware to support many different experiments. So FPGAs, many different types of GPUs from, let's say, RTXs, which are gaming GPUs, to A100s, interesting networking hardware, and so forth. And over time, Chameleon, the 2 main operating sites, were joined by multiple volunteer sites that are using the Chameleon packaging of its infrastructure to add resources. And then most of us know Chameleons like to change. So the system was named after the capability to adapt itself to your experimental needs. So we use right now 3 different types of adaptation. One is reconfiguration at bare metal, where the nodes are re-imaged and rebooted. And then we also can reconfigure nodes by deploying virtual machines. And when we use edge hardware, we do that by deploying containers. So you see that small autonomous vehicle in the corner there, we'll reconfigure those by container deployment. So in addition to this edge to cloud continuum, we also have a continuum of different configuration methods that allow users to program those devices. Most of Chameleon is based on a mainstream system, and you'll see in the rest of my talk, we're very much believing mainstream. So mainstream cloud system called OpenStack, which we modified significantly. Some of those changes were contributed back to OpenStack. So in particular, we played a key role in the development of an advanced reservations component called Blazor. And then some of them were not relevant to OpenStack. They're just specific to our use case, and they're available as open source, but not contributed back necessarily. And then we also believe that our community will be more productive if we allow them to share digital artifacts like images, like Jupyter notebooks. So we provide a programmatic interface to the testbed, which is also available via Jupyter, and places various repositories where you can share your digital artifacts. And one thing I wanted to say right up front is that I'm very happy to be part of this effort, because we've had a long-standing, almost 2 decades long collaboration with a fantastic INRIA project called Grid 5000, which developed many of the ideas and approaches that Chameleon ultimately adopted, and we adopted some of the software they developed as well. So we're definitely looking forward to more of that. Chameleon, by the numbers, just last year, we celebrated our 8th birthday. we took some liberties with the logo to celebrate. But the main point I wanted to make is that over those 8 years, we served more than 9,000 users working on over 1,000 projects in computer science research, computer science education, and in emergent applications, right? So new innovative applications that are pioneering new ways of using hardware. Over that time, our community produced more than 600 papers, so there were significant research impacts from that. This is just a quick overview of the Chameleon hardware. So you can see that, like I said, we've got all sorts of strange and wonderful hardware, GPUs, FPGAs, all sorts of different storage solutions so that our users can mix and match and experiment with them. And we do everything from stuff in data centers, so at relatively large scales, to edge devices like Raspberry Pis and Jetson Nanos, and more about that later. And we've got several volunteer sites. We created something called Chi in a Box that allows sites to add their hardware very quickly. And that's being done now both to add resources to Chameleon on a permanent basis, but also to, for example, support student competitions on an ephemeral basis, right? So because that action is very quick, it can be done. It can be amortized very quickly as well. And we collaborate with some other NSF-funded testbeds, in particular the Fabric testbed, which is a fabulous networking testbed. So we've got both data centers and edge, and the networks that go between those things. The Fabric PI is a co-PI on Chameleon, and there's also a range of NSF-funded wireless testbeds, which are fantastic partners as well. This is a quick overview of the workflow of how you program Chameleon. So from resource discovery, where we did adopt a lot of Grid 5000 ideas, to allocations, to reconfiguration. I would just call out, we support on-demand access like any other cloud, but we also support advanced reservations. So in particular for our GPU resources, it's a feature that many of our users appreciate. And then for interfaces, we support access via GUI, via command line interface, and programmatic access via a library called Python Chi. So if you're setting up your experimental topology or experimental environment on Chameleon, you can just simply write a program and then rerun that program, which is very important for reproducibility purposes. Our Jupyter interface to the testbed has both Python and Bash kernels. So you can use both command line interface and Python to program the testbed. Chi in a Box is a packaging of our infrastructure. I mentioned earlier that allowed us to add multiple volunteer sites to the testbed. It allows us to support projects on an ephemeral basis, but it also allows others to adopt our infrastructure easily. And in particular, there's an NSF-funded testbed called ARA. It's a wireless testbed. They adopted our Chi at Edge infrastructure, which I will talk about next, which manages edge devices, and they adopted that to create their own testbed, which is fantastic from the perspective of collaboration, because whatever solutions they develop in wireless will be extremely easy now in turn for us to adopt. So that was a very good collaboration. Now, several years ago, some of our users started signaling to us that they are interested increasingly in working at the edge. So they worked on things like network fingerprinting and federated learning projects. And it was increasingly important to support edge devices. And after some back and forth with the community, we settled on an approach that really looked very much like Chameleon, but it deployed containers on edge devices instead of reconfiguring them on bare metal, that had the capability to manage IoT peripherals. But the main difference, the very significant thing, was that many of our users were not really interested in using devices that we provide. They wanted to use their own edge devices that are attached to their cameras, which is deployed somewhere and looking at interesting things, or environmental sensors, or things that are very location specific. So we developed a paradigm called Bring Your Own Device, which allows our users to add their devices to the testbed for limited sharing. So for example, if you are running an autonomous driving class, you can add your cars, which are connected presumably to some Raspberry Pi or Nano. that's what happens in practice. And then add them for limited sharing, so just for the class, right? So if you're not collocated with those devices, might not make sense for you to use them. And then this is not technically part of Chameleon, but SHE@EDGE gave rise to a project called FLOTO, which is an instrument for broadband measurements. It was brought up by one of our users, and it's really a very streamlined version of SHE@EDGE with some data processing mechanisms. And it deploys 1,000 devices over various municipalities that you have listed there, as well as university of campuses, and supports other research projects. So at this point, we've got hundreds of devices deployed that we're managing, that we're using to run broadband tests. Where they are deployed is used in broadband research, but also in policy decision-making and in broadband modeling as well. And then just recently, we actually got some of our devices back. So this is a very interesting thing where if you want to do a project, we ship you some devices, then you ship them back after you're done with your research objectives, and we can use them for something else. And just very quickly, we're very interested in promoting practical reproducibility, so making our user community more productive. And we invested in services that help our users package experiments in such a way that they can be shared easily. We have Trovi, which is a repository that of those experiments that is integrated with Chameleon. It's a little bit like Google Colab, if any of you use that. And we give access to users using the Chameleon Day Pass. So specifically, that's access for reproducibility. So last year, we've seen a huge surge in usage for reproducibility. It's hard to measure those things, but as a sort of rule of thumb measure, roughly almost 7 times more in 2023 than in 2022. So here is a quick collage of various pictures of our users in action working in their labs, working on as part of various student competitions, giving presentations, and so on. So to wrap up, Chameleon is a cloud, a testbed that evolves as the scientific frontier advances, because people create new experiments that we then have to provide a tool for, which is fantastic. We promote reproducibility, and we have a lot of experience in not just building reliable infrastructures, edge-to-cloud infrastructures, but also building very happy and productive communities that use those infrastructures, right? So we work with thousands of users and many different use cases. So thank you. Happy to take questions.
Thank you very much, Kate. So we have time for 2 short questions.
I have a question.
So, Quinn,
yes,
please.
I have a question. You have a large community. Is that community meeting from time to time? Is there a workshop will linked?
Yes. So if you go to the main Chameleon webpage, you will see a link to our last workshop, which had special emphasis on education. We usually run those community meetings about 18 months apart. That's another thing, another blueprint that we borrowed from Grid 5000, so 18 months apart. So that's one was focused on education. During the talk, I mentioned a report from an earlier community meeting, which was focused on Edge specifically. So yes, and you know, if you go to our webpage, you will see. Okay.
I'll check it out.
And I see that, yeah, Thomas has his hand up.
Yeah, a very quick question. You listed all the devices. What is the most low-end device that you support? I have a hard time kind of seeing.
Raspberry Pi 4.
Raspberry Pi 4, great.
Yeah, so they are all, you know, for our Edge devices, we roughly assume that it's something that's going to run Linux, and then anything else is a peripheral that we add to those devices.
To those devices, yeah. Excellent, excellent. Thank you so much.
One question from me, Kate. You presented an integration with Zenodo. So you are using for integrating your publication, or what kind of
for integrating the publication, so I mentioned the Trovi repository that is integrated with Chameleon. It does have a backend to Zenodo, right? So if you write an experiment, we write typically that looks like a Jupyter notebook that is annotated with your insights. Trovi really was created because users wanted to iterate on those on work in progress. But once you have a digital artifact that represents a result, that can be published to Zenodo. And so we provide sort of one-click interface to doing that.
Very interesting. Maybe we can adopt this as well for this community. So we use your
absolutely. Let's talk.
Exactly.
Okay, we're interested in collaborating both ways, right? Both adopting your ideas and you know, making whatever we have available.
Thank you, Kate. So then let's move to, again, we try to see if Filippo.
Yeah, otherwise, can you hear me now?
Yes.
Okay, it's strange that when I start sharing, I stop my audio, but there is my colleague, say, Dan, who is the technical manager of the project. So maybe we can try this time if Dan can make it.
Okay, here. So do you want to try, or I will give the presentation on your
in order to save time, maybe if you are available, and maybe it's
okay.
Because when I start sharing, it's stop the audio. I don't know why.
I can share too.
Technology.
If you just tell me when to move. Okay.
Okay, I get. Everybody can see my screen. Okay, that's good. So then, because Filippo had a problem, then on behalf of the project, I'm going to present SMARTEDGE. So the SMARTEDGE started last year, not this year. So our project is on building semantic local programming tool for ad intelligence. So the budget is 7.4 million, but we have a UK situation that they become associate partner with ToolSuite partner. So our solution is try to make the programming, the intelligent on the ad easier and less painful, and then scale better. So we build a consortium from two core communities, people doing data integration, which is working higher level of abstracting, seeing data, how to continuously integrating data from multimodal data, a different standard, and orchestrating that on Swarm Intelligent Edge. But when the workload run on ad device, they need connection and then network programmability on different hardware device, from wireless to wire networks, and V2X as well for the vehicle use case that I'm going to present. So then we use network programmability like P4 language to be able to form the network dynamically to create data link to route information where it needed and control the bandwidth, and also upload processing to the script if needed for some high demanding, not only bandwidth and AI operation. So in the middle, so that combined with some our proposed declarative programming models. So we integrate these two pillars together to make a set of two chains, so that the programming, all the use case that we propose, faster and tested in several domains. Actually, in terms of use case, we have 5 use cases, but in here we're going to present 2 use cases that mostly related to Swarm Intelligence. So the first use case on mobility. So actually, we have a test site in Helsinki where we test with a car company and the city who operating two sides of spectrum of mobility is who maintain the roadside unit, who have eyes on the road and control that traffic light. And the other part of the swarm is the road users. This is we focus on car. So the car have to communicate each other to move safely and smooth cruise control. They only can have a limited life size, so they need the information from the other vehicles. And the same with traffic light, they also have the sensor from ranging from LiDAR cameras or only look detector on the road. So they have different modality of the data. It will be really expensive just them to send pairwise. So we come up with an idea called semantic stream. That means the stream after extracting from AI operation to make it smaller in semantic sense. For example, the counter say I might to stop to red, or the light say I'm going to red in few seconds. You shouldn't overtake this and go to safe zone and this kind of thing. So basically, the swarm of vehicle and light can do pairwise exchange via V2X protocol and other wireless protocol in really light way. But we'll have with AI, we extract the right information and send to the right one at the right time. So the effective of that, we're going to then demonstrate in a district in Helsinki, where they have around like 8 intersections and several camera LiDAR around, and we have vehicle moving around the city sharing information. And this system need from cellular network to in-car network system and roadside unit talking together. And we were able to do that in the local fashion. The second use case, we do a smart factory. Actually, we have 2 smart factories, one in Ireland and one in Germany. But the similar concept that focus on the swarm is even now the sensors getting cheaper, processing on it also getting cheaper. There's a lot of possibility to do intelligent processing to share the perception for the vehicle, for the robot to move around, for them to navigate, to exchange tasks and collaborate. But in the end, for manufacturing or the operational operation body like Dell factory or Siemens factory, they need to reduce the cost, not only the sensor and processing unit and robot, but also the operational cost via bandwidth and power and these kind of things. So we don't see the need that every robot or every part of the factory floor need to have LiDAR LiDAR or camera, or the powerful processing like just an Onion or something like the edge computing server, but they can collaborate to share perception like slam up or together, so that to reduce the cost to use a wide range of gateway from Raspberry Pi Zero or to Jetson Nano, and but they still can program it in based on the goal on the task set to a high level, and the system will find a way to optimize from local perspective by specifying the goal or the manufacturing line from business standpoint, and the optimization will be done by the tool chain. So the swarm effect, like what we've been established in swarm computing, is we extend or the model of swarm computing to be able to programming at high level of the task and the goal. From that, we break down what we call recipe, is kind of self-service computing to plan or set the goal for the whole swarm of the robot with different hardware capability and networking, then give it to the system to be self-optimized and driven at the swarm intelligence spec. in this swan computing paradigm. So that is the two use case that we're going to demonstrate from this year and next year for the project. So now I'm happy to take the questions.
Thank you very much. So questions to Dan and Filippo? Maybe I start to break the ice. So for the V2X implementation, what kind of technology you are using?
So currently we use the available onboard unit provided by the cell, but what we do is we use the V2X relay gateway connect between vehicle to vehicle and vehicle and roadside unit on the road, and we abstract with other networking stack that we program via P4 so that when you send the data, this thing will abstract from two levels with the AI operation in between to do data optimization and the other things. So basically, we didn't change the stack of the protocol in V2X, but we abstracted to data processing and incorporate with INCODE network.
Right. So then I understand that you are using the existing technology based on 800 and 211p wireless technology. Right. Okay. Other questions?
Hi, this is Deepu from UCD. I have a few questions. I was looking at your website so you have use case on healthcare, and you're mentioning multimodal fusion. So is there a specific application or specific healthcare use case where you want to use this technology?
I think healthcare, we have two actually sub use case. One is for monitoring the rehabilitation home, and one for rehabilitation for center for people monitoring wearable with ad hoc sensor network, and then maybe have a camera and the other motion sensors, and they want to share with others. Then we incorporate this kind of stack. The others to monitor elderly healthcare home. Also, they also have some ad hoc network, and then collect data. We connect to some gateway, and then we abstract from perspective of what information is needed. For example, like the situation people monitor in outbreak, and this thing to know where the person is and where to sample some I think distant tracking information via a mix of between localization and visual sensor together.
Thank you.
So thank you very much, Dan, and thank you very much, Filippo. So now I invite Manish to present IGAR.
Sure. Daniel, can you share the slides, please? Can you have the updated version? While he's setting it up, and IGAR, as I mentioned, is an exploratory project, and this specific project is to really explore how we can use edge platforms such as Sage, which you'll hear about next, to enable applications. This is part of a broader project that we've been working, our group at the Scientific Computing and Imaging Institute, along with Daniel, who's now at INRIA NANS. We've been working on how do you build programming systems and runtime systems to support applications across the continuum. We're not seeing the presentation, we're seeing the...
We're seeing the... Yeah.
Perfect. Can you go to the next slide? So I won't spend too much time here. I think the introductory talks made a very good case about the fact that we have a computing continuum, and especially in the scientific computing space, right, in the area of scientific discovery, we have a continuum when we take the spectrum from large-scale instruments and data sources along with resources along the network, at the edge, in the fog, and large-scale cloud or HPC data centers. If you can use them collectively, we can imagine end-to-end applications that can really close the loop by acquiring data real time, actuating, analyzing that data, using it with predictive models, whether computational or data-driven, and then using the continuum to actuate and make decisions. And a lot of the applications that were presented have this really approach to it, right? We are looking at this more broadly, but we are really focusing on one class of such applications. Next slide, please. Which we are calling urgent computing. And the idea is, can we do this in scenarios where there are strict time and quality constraints that can support decision making in terms of some urgent scenario, right? Some sort of a, trying to make a decision when you're addressing forest fires, or you're trying to make a decision and actuate when you're trying to address, say, a hurricane or an earthquake, right, where there is a time criticality, and that may vary, and there's an urgency, and these are exceptions, right? This is not regular operation, but this is some exceptional scenario that happens in the presence of some sort of an emergency, right? One motivation of this came out with what happened during the pandemic and some of the things around it. So one example out here is a wildfire and the impact of wildfires on air quality, which is something for a local challenge in Utah due to the geographical layout of the valley and phenomena such as temperature inversion, and this has tremendous health effects, whether it is respiratory health, whether it is reproductive health, cardiovascular health, and it also been tied to things like mental health and leading to things like high suicide rates and the like. And so we're trying to see how we can leverage the continuum to be able to detect using models, using data coming from multiple sources, using data-driven models about the progression of the fire, the weather conditions, progression of or air quality models, bring them all together to be able to predict. And because of the way this happens, right, it happens very quickly. It can be viewed as an urgent scenario. We have very little time between the perfect conditions where fires far away can actually impact our valley here in Salt Lake. So in terms of implementation, we are building it on top of a bunch of existing platforms, such as SAGE, which you'll hear about in the next talk, Wi-Fi, which is a wildfire simulation and a data simulation project at San Diego, and a lot of work on air pollution and air quality modeling. And how do we connect them together across the continuum with real-time data sensing? So at this point, with this broader framing, I'm going to hand it over to Daniel to talk about the research problems and maybe dig deep into one of the research solutions that we are building.
Sure. So still with the large research challenge associated to this project, the overall goal of building intelligent services was to provide some kind of blueprint for urgent applications. So we explore this through 3 different research challenges. The first one is to understand the availability and efficiency of the continuum. At the time you're developing the application, you don't know what kind of resources will be available. So to compose with what is available, being able to generate trade-offs, we explore some model to be able to extract some efficiency of the platform. What will I be able to do? What kind of error can I tolerate in a particular configuration? Assuming that our application can adapt to that available platform, on the DevOps or developer side, we want to offer programming abstraction for implementing those applications. On the high level, once you abstract the infrastructure and you want to have some kind of API, some high-level abstraction, so that we can program that kind of application, how we will get the resources, but also what application logic is best suited at this moment. If your application is mostly executing at the edge at a time, you might not be using the same library that you will do in the cloud. And this is something that you find or you have to trade at runtime. But from the developer perspective, this is something that should be abstracted if we want that continuum to be leveraged. So this happened in our middleware at runtime. We will show that in the next slide. And finally, the third slide, considering that we don't want to extend the cloud or start thinking directly at the edge, but really for the continuum as a whole, is to see how can we have consistent decision across that continuum. If I'm at the edge and my device is losing connectivity, what should I do with the data that I have? Keeping it for later, hoping the network will come, try to reduce the quality, and those decisions that I'm taking in an isolated fashion might not be the best for the rest of the federation. So there is a need to have that kind of consistency, and we're trying to think about that control layer while keeping it effective across the compute, storage, energy, and so on dimension. There is multiple projects as key associated to that around those three different questions: how to drive computation through data, being able to discover and aggregate resources based on current need, but also at runtime, being able to manage some quality of service and performing such trade-offs. Some link and reference associated to the different people that works on this project. The slide will be shared in the video, so you can look at them individually. I want to insist on the project that we move forward during this year, which is the airPulsar middleware, with the idea of providing programming support for data-driven workflow. What, where, and when will I execute my analytics, and providing API or rule-based engine for that. And finally, on the system perspective, being able to allow device to behave naturally, if I can say, so that they can come and go in the federation while making sure that we keep the data and we maintain the quality of service. One abstractive way to see this middleware from the developer perspective is that we combine producer of information, and namely we're thinking about the Sage platform, where we will write rules so that we can collect data associated to filters based on threshold, statistical train, streaming windows, and associate action that will be evaluated at runtime and triggered in a data-driven way. If all my resources are available, there is something I can do, and it's easy to solve that constraint. But once things gets complicated in an urgent situation, something you could not fully plan, what can I do and what kind of action will allow that application to work in a limited mode? I will finish with application example. So one of the domains for urgent computing is disaster management and scientific computing. We made a lot of work around earthquake early warning, and we use that project to also, how can I say, incubate some contribution and attract domain scientists that are not usually thinking toward the continuum or not using its full potential. This project starts with a new model for earthquake early warning, when we can use multiple sources of data. And on top of this, being able to maintain property of resiliency, latency, energy as well, so that application, that model that was once centralized, can now be deployed across the continuum with all that flexibility that comes with the edge, but also being resilient to partial infrastructure damage, which is not something you think about when you develop the AI model if you are earthquake scientist, but something you want in production when you will deploy it on a platform that maybe will evolve or is not existing at the time you develop the model. So overall, being able to leverage the computing continuum for preserving that kind of metrics, latency, resiliency, and so on. Thank you for listening, and we'll be happy to take questions at this point.
Thank you very much to both of you. And now we have time for 2 short questions.
I see John with the raised hand.
Maybe you can
Yes,
stop
please.
sharing.
Hello, can you hear me?
Yes.
Okay, since we are talking about, I guess, disasters or PPDR applications, and I guess with this you have some restrictions, you have some requirements, as you said, and I presume that you cannot rely on let's say, public networks like commercial 5G. So in such occasions of disasters like wildfires or earthquakes, what alternatives for communicating, for passing the data from sensors, cameras to, let's say, to edge node or cloud do you use?
So I think that's an excellent question, right? And I think the way where we are focusing right today is to be able to program applications that can detect and react to that situation, right? And how you react to it depends on the specific application, right? There could be places where you could make decisions with with approximate data using models. You could use alternate solutions. So what we're trying to do in this project is, given the scenario where you have uncertainties, and one of the uncertainty is the physical infrastructure itself, right? How do you program contingencies to that? Right? So that's the focus. Now, the exact solution will depend on the particular scenario. For example, do you have alternate communication means, if the broadband goes down, right? And how do you switch to that? So we're not building those solutions, but we're building applications that can incorporate alternates if there exist in such a scenario. Does that make sense?
Yeah, thank you. Because our project also foresees some scenarios, a PPDR scenario, in which we include the communication of UAVs, for example, to detect people. And we also have a scenario that we don't have to rely on commercial 5G. So we try to find solution alternatives so as to successfully carry out this scenario.
Right. And so here we are allowing you to pick one of those alternatives depending on different situations that might exist. And Pete is putting it in the chat. For example, Sage provides different options. We could program applications that might say that if you find that this has gone down and this situation, then react to it by using this alternate mechanism at a lower data resolution, just to give you an example.
Thank you very much.
Thank you very much. So do you have other questions?
Ovidio, I would
Yes.
like to ask maybe the project, because the early warning of the earthquake sounds really like a breakthrough, but the difference with other use cases is the time. Yeah? So if I would like to ask about the time and dimension between detecting this danger and providing this warning to how much in advance to the public.
Right. So Daniel, you want to take that for the early earthquake warning?
I'll take this one based on the actual data set that we use for that validation. So the window was something like a couple of minutes. which was the time it takes for the data to go on the top right from the data production to do the first regional level, then aggregate that information before broadcasting it. So basically, that is the time we had to increase the confidence in the event, because when that happened, we actually detect the event in multiple different places. So some will say, okay, there is a 5% confidence, and we need to match that result with the other area that detect it at 75%. So this is the kind of work we are trying to do during that window. I guess there is data set with even more data constraint, but we wanted to see what we could do in that window of time for a real data set.
So it's several minutes.
It's several minutes, yeah.
Okay, thanks. Very interesting.
Yes, indeed, very interesting and very hot topic as considering the event in Japan. So this is an area that needs more research and more investment. Thank you very much. So then let's move to the next presentation from Pete and Nicola, presenting the SAGE project.
Okay, can you see the screen here? I believe so. So yes, Manish and Danielle mentioned SAGE, so I'll go ahead and start. Nicola and I work on a project which is funded by the National Science Foundation, and its primary focus is on edge and AI in particular. And so this model that Manish and others have pointed to, this computing continuum, is something the NSF has been exploring and pushing forward on. You heard it in the intro. The idea that all the way from the instrument to the supercomputer or to the cloud, there is a computing path, and there are discrete places along that path that computation can occur. And so many of the presentations today had, you know, whether it's in a factory or somewhere else, computing happening at those devices. And so we're focused specifically on scientific instrumentation in our project, although not to the exclusion of others, but we're focused especially on areas where it's either climate or AI research and algorithms. What can be moved out to the edge, and how would that work? And one of the key advantages to moving that AI computation out to the edge, as the previous discussions have outlined, is latency and response, as well as analyzing the full resolution. So normally in these old-fashioned networks, like what you see on the screen here with a tower and a hut on the left, that would send data every few minutes, and it would be a summarization of the data because they didn't possibly have enough bandwidth to send it all. But by putting computation at the edge, we can do that. We can process that data right there using AI techniques. And so SAGE built a national cyber infrastructure. It's deployed in Oregon, in Utah, in Colorado, in Illinois, in Hawaii, and other places. It's a place to run code and test ideas, test algorithms, but also develop new computing continuum paradigms like our pulsar, right? How would you do urgent with this kind of mechanism? So when we talk about running code out at the edge, what does that look like? Well, it could be a variety of topics, and every science community we've talked to has a different approach or thing they want to do. Everything from understanding plants and what kind of plant species or bird song. We have nodes that are in a prairie, in the forest, and are analyzing automatically at the edge what birds we're hearing. Wildlife, traffic and cars, wildfire and smoke detection. All of these are software components that can be pushed out and run in this infrastructure. And the infrastructure is both hardware or software. It can be either. So there are places that are pure software. We're just deploying containers onto rack-mounted or small devices that are hosted by the community. Or we can help and provide a node which is weatherproof and sits outside. So this is a sort of an overview of the kinds of algorithms that different communities are developing AI algorithms to run at the edge. So if you look here in the left-hand column, if you're a scientist interested in traffic state analysis, then there's a number of algorithms that you might apply, and we have test examples that I'll show you in a moment. Or estimating the water depth from a stick that's in the water, or looking at solar irradiance. We have a project that was mentioned earlier, similar to measuring cloud motion so that we know when clouds are going to go over photovoltaics. So that's a cloud cover and a cloud motion vector. And that's deployed in various parts in the United States now. In Oklahoma is where some of the cloud work is done. Sound. And these are the different AI methods that are being used, and then where those things are run. And I have down here as a picture, just an example. This is at a Native American reservation, and they wanted to measure snow coverage. Of course, in this image, everything is covered by snow. But as the river begins to freeze over, that kind of automatic calculation in real time is important. And I wanted to just throw this in that this is a unique project in that it's focused on AI and enablement of ideas in the computer science space, but we do that with real deployments, right? So we have this odd link of, no, we really are going to deploy out in the wild, and this was a deployment we did in October, and those are students from Indiana, or from University of Illinois and Northwestern, not climbing the tower, but the students are at the bottom, setting up the node. And that node is now ready to run AI codes and for people to test. Now, it looks very similar to what you might imagine. What was mentioned earlier is whether it's a pure software piece built on software that has nodes already deployed, or we have to deploy something that is physical because it's going to sit outside. But a piece of container code that runs AI is shipped out to the edge and then can be run. Now, some of the key features here that are unique is that it has to be a multi-tenancy. We want multiple research groups to be able to use the node. So in this case, for Hawaii, there are several groups who want to be able to write and run code at the edge. So there's a kind of scheduler that has to be able to manage that. And there's also local actuation, moving the cameras or modifying experiments. So I'm going to do a quick, I'll say demo, a quick shift to show the interface here for a moment. But how we might collaborate with Europe. Well, we have nodes all over the US. We only have one in Scotland, which some of you may say doesn't count as Europe. But we would love to, with the idea of an exchange where we've had someone from Italy come before and work at the lab for a summer. We've already been speaking with Rosa about, and we started at Supercomputing in November, talking about how we might do a test deployment with some AI codes in Spain. So we'd love to work together. And as Manish and Danielle pointed out, new programming models are going to be key to this. We've built some, I'll say, plumbing and AI innovation, but now how to string that all together is a really great open question. It looks like a lot of the projects currently in Europe are more end-to-end in that way. So I'm going to try a little test here. Let's see. I'm going to see if we can share this. Okay, so this is the portal. There's a regular sort of website which shows the project and so forth, but this is diving down into the portal of actual nodes. And we have a catalog here of applications that you might run out at the edge. So that wildfire detection code was updated 6 days ago. It's interesting. I didn't know they were still working on that piece, updating that piece of code. That's great. And if you looked at any one of these codes that you can run out at the edge, there's a background on the code, but there's also all the GitHub information of how to run that code and what to do with that code. But if we go back here and we look at the United States, we might look, this is the one that I said is Utah, but it's actually deployed in Montana. But it is the Utah node, and we'll look here, and we can see that the job schedulers running all of these jobs. So these would be things that students or postdocs have designed AI codes to run at the edge. So that cloud cover that we talked about, like for solar panels or other computation, the avian diversity, what birds are you hearing? All of those codes are running, and we can look here at the images from Montana right now, and there's an infrared camera as well. And if we, looked at, we were looking earlier at the images from the Hawaii node, and of course, I think it is not quite morning there, so I don't know that we'll see if we can do this. Let's see if we see anything interesting there. Yeah, it's still nighttime in Hawaii, so we're seeing dark, but this is looking down at the canopy, and we can even listen to the audio. But again, the point of all of these applications is to be able to do and test and explore AI and continuum programming models in a real situation, a real life deployment across the country and other places, and then to use that research to build and explore what does the future look like. We get, of course, real science measurements, but does the future look like as we reprogram and write code that lives all the way down in battery-powered devices? And so we have some lightweight things, LoRaWAN and others that are connected to nodes as well. So with that, I'll open it up for questions.
Thank you very much, Pete. So we have time for very short questions.
And Nicola, as I said, Nicola leads the AI portfolio. So if there are AI questions, Nicola can probably dive in to talk about either federated learning or distributed topics, self-supervised learning.
More than a question is a comment, because we have seen both Chameleon and SAGE provide infrastructures that can be used as test beds for the European projects, no, and as be seats for collaborations, no. As Pete mentioned, we were discussing a possible deployment in Spain, and as he said, well, it can be a simple deployment of SAGE, but also it can be a more wide collaboration, no, between the two different groups, no, and this a little bit is, I think, is what Discover Us can help on making real, no. That would be great.
And we, as I said, I think it was last summer, we had somebody from Italy visiting, and when it was mentioned earlier that there's a way to do exchange, that might be a perfect way for, either one of our postdocs or students to go and visit you, or vice versa. There are a lot of opportunities, I think, that opens up.
Can I have a question? So you might find the option to raise the hand. So you say that your testbed can involve more partner to provide data or participate in experiment setup. Could you elaborate more? Because, for example, in our project, we have some partner from public body like the city and open some campus system for having similar data like yours in Europe. They are willing to provide the data for open science and this kind of thing. So could you elaborate with the mode of operation? And
no, a very good question. So there are, so if it's a group is just, I'll say, providing data, then there are two ways to collaborate. One is that a method that we can look at, one of our partners in San Diego, is how is that data presented together? So if it's real-time data, like in some cases, there are places where there are deployments of data that you want to fuse together other data sources in real time, right? So that kind of putting two data streams together is something that San Diego has more experience with, but is a partner, and we would connect up. But the other method is just in the AI algorithm. So, sharing data. I mean, it turns out that students who are working on AI problems, there's enormous lift initially of finding a data set and getting it working and getting it cleaned and getting it ready for AI. And so if there are data sets that that are open that allow for that and that students have already worked on and cleaned and prepared, that would be great. We've only just started exploring, like maybe we should be as a community putting all our data and making it available on Hugging Face. We've done a couple simple tests of that, but is that something that as a community between Europe and the US we might explore, as putting training data together so that students can get going and work on shared data sets?
I know that the time only allow one question, but I think one thing I just comment and also the point of discussion is sharing data in Europe is quite different in terms of regulation. For example, we work with city, we still work in the process of have go through different policy, going to the lawyer to see where even within a partner, and then how to do it public, even contractually with the commission, we should back some part data to public, to beneficial, especially in mobility domain, is the car company would like to get the data from the city to train the model for severe situation, and this kind of really helpful. But within this US and Europe collaboration, sharing data from the ad to that, it needs some discussion how we can do that, because yeah, open science is look the kind of good deed, but I get the legal liability also catching up, even for the researcher doing not for profit purpose.
This can be addressed, thanks Dan, this can be addressed during the project, because I think there is an interest for the community in Europe to have as many open data sets for training and extend the data sets that are collected in Europe with the data sets that are collected in US. This will be extremely beneficial for the community. But Rolf, you have a question.
Yeah, and first of all, thanks, Peter, for the genuine presentation. It's really interesting. I noted two things. First, your interest in offer to deploy more programming, to deploy more nodes even in Europe, and then to ask people to experiment with that one. I think in the Commission we have a certain deployment programs. We also go for pilots. So I think I will keep it in mind and to see which of the projects are running, which sort of pilots are coming up in the area and different areas. For instance, I could imagine farming, where people would be keen to experiment with the nodes and to see, how fast you can download and experiment with the apps. And the other part I wanted to emphasize is that in the area of cloud edge IoT, we're definitely promoting this idea of having an open app store at the edge. I think we have seen examples in manufacturing. You've shown examples for environmental monitoring, for traffic monitoring, for farming. I think we need to promote these use cases, because on the one hand, it gives you really technical, a powerful technical tool to work with that, to exploit AI. But on the other hand, it's a complete new way of exploiting an open ecosystem. And I think we have to keep that example in mind and have to see, if we can use that good practice either to deploy nodes in Europe, or to use that principle, also to apply to other projects. Could be on AI algorithms, could be on different apps which have different functionality, which deploy functionality. But the main principle is quite groundbreaking. Thanks so much.
And one note to follow up is I forgot to mention, we're also very interested in collaborating, and we've already started some discussions on AI ethics with respect to this. So we know that how we use AI, people are very concerned about that in the United States, and Manish may know more, but this AI executive order talks about privacy enhancing technologies, PET. Those are things that we want to bake into the AI, and as I said, Nicola could talk more about with federated learning, the things we've learned already. But that ethics and how to be completely transparent in the AI is something that we very much want to collaborate with.
So then welcome to Europe, Peter. So explainability and interpretability of AI solution is one of the priorities. So very, very important.
Indeed.
So then, in order to keep the time, we have the last presentation from Dimitrios or from Deepu. I don't know who will present the suite project.
Hi everyone, can you hear me? And
yes.
see the
Hello,
screen?
yes, we can hear you.
Yeah. Okay, so our project is the suite project. So this is a US-Ireland consortium project, and funded by so the three partners one from Virginia Tech in the US, and Queen's University, Dr. Hans from Queen's University Belfast from the Northern Ireland, UK, and myself from UCD Dublin. And so we are just starting the project maybe a couple of months back, and the project is on very similar lines as some of the discussions that already happened. So probably I'll go to the second slide first. So our project is mainly about how we can distribute an AI model across multiple nodes in a system. I think we heard the presentations from many people before. So we have the IoT node, and we have the edge server. In our case, it's a smartphone. We assume it is a smartphone, and we have the cloud. So previously, all the applications were cloud native applications, and obviously the advantage of edge AI is very promising. And therefore, what we're trying to do is how we can take advantage of both the edge AI approach, or the edge native computing, and the cloud native computing. So the context of our project is very specific to healthcare. So there are a couple of reasons why healthcare or IoT wearable sensors is an interesting application for this kind of distributed AI inferencing. So the first reason is that if you use continuous streaming from an IoT sensor to the cloud, the battery of that wearable sensor, the IoT sensor, will drain out very fast. You get 1 day max of battery life. And that would mean the ability of, or the diagnostic yield of that biomedical data will be very low. So the other option is you can try to deploy the model entirely on the edge sensor. Then we have the problem, you have very large models. You want to you can say the accuracy of your model is kind of proportional to your the model size, and you cannot deploy very large models on the edge. So we have this problem, either if you send the data to the cloud, you have very low battery life, and you cannot deploy large models on the edge. And you also have this problem of connectivity. In our case, if you use, let's say, cellular networks or 4G networks or Wi-Fi to connect to the cloud, and if you're moving with a wearable device, sometimes you may not have that connection. There are areas where you have low connectivity. Or if you use your smartphone to relay that data from the sensor to the cloud, sometimes your smartphone can run out of battery. What will you do then? So this kind of uncertainty in that connection, in that edge to cloud continuum is also there. So how do we deal with that uncertainty? So what if you get a medical condition when your cell phone battery is drained out? You cannot get any whatsoever response from this kind of system. So our project is trying to address all these different problems, which are specific to the wearable health sensing use case. But again, as we discussed before, we try to solve this using the distributed AI approach. So there are three main partners of the project. That is myself. I'm working on the edge AI part, edge accelerator part. So in this part, what we do is we develop an AI accelerator, which is similar to some of the commercial products that is available, but there is a difference. And I will be working on the AI accelerator part, where I'll be developing a RISC-V based AI accelerator to deploy these models. And then we have Dr. Hans from Queen's University Belfast. He'll be working on transprecise computing or distribution of AI models onto different devices based on real-time use cases. For example, if there is a cellular connection available, or if there is a Bluetooth available, or what is the signal to noise ratio currently on the network. So based on the current situations on the ground, And we try to distribute that model, and Dr. Hans is working on that. And Demetrios is working on deploying this serverless computing on the edge infrastructure. And there's another collaborator from Virginia Tech as well. His name is Dr. Bo. So in terms of the AI accelerator, although there are several accelerators on the market, so there are some differences in what we are trying to build. One of the main differences what we are looking at is to build an accelerator for generalized or generalized hardware. So we have different types of workloads, CNN workloads, RNN workloads, or the new transformer kind of workloads, graph networks. So one of the novelty of our hardware is our hardware can work on all of these different kind of models simultaneously. And we also tweak our hardware to support what we call as a dynamic neural network, which includes things like early exits, multi-precision computing, etc. So our hardware can also support variable precision quantization. For example, if your battery of your cell phone is about to drain out, you can extend the battery life of your entire system by reducing the precision. So based on the real-time condition, you can reduce the precision and still have something like a graceful degradation. So that is something we're looking at. So in order to support that, the hardware or the accelerator will support variable precision, where you can reduce the quantization bitwidth or adjust the quantization bitwidth. And we also support something called on-chip hardware compression, because one of the challenges with the AI accelerator is what we call as the power consumption or the memory wall. You need to transfer a lot of data between the RAM or the weights from the RAM to the compute kernel. So we have some proposal on how we can address this issue by reducing or compressing the data on chip before you transfer the weights across the RAM and the compute kernel. So this will be, so we are trying to use a RISC-V based processor. So RISC-V, as you probably know, is an open instruction based processor, and you can develop your own instruction, which is a key advantage in this use case, because we need to dynamically vary the model that is being executed on the IoT sensor. So if you have a fixed data path model, then you can use something like a programmable or like a memory mapped peripheral kind of an approach. But in our use case, we need to dynamically vary the data path of the model, and therefore having this RISC-V based approach helps us to change the instruction sets of the entire system on chip. So that is one of the component of our work. The second component of the work is again done by Dr. Hans from Queen's Belfast. So he is focusing on the modeling of or developing how we can distribute the model across multiple devices based on the current quality of or the required quality of system and the current ground truth data, and how to deploy those parts of the model, how to distribute different parts of a single model, possibly, or different types of models across different nodes in real time, and how to tune the inference models for continuous telemetry. So how to vary the precision to support dynamic requirements such as the battery life, or the if you have the signal, or if you have the channel conditions of the wireless channel is good or bad, how to vary the precision. So that is the second part of this project. And third part of this project is executed by Demetrios and Dr. Bo from Virginia Tech. So this part of the project is focused on how you can deploy a variable precision model on the cloud. So cloudless inference using WebAssembly. So Dr. Demetrios is also trying to looking at deploying parts of the model as virtual machines on the IoT sensor, or on the smartphone, or on the cloud. We are using Amazon Web Services for our cloud service. And he's also working on approximate caching techniques for inference models. This is again another approach of dynamic neural networks. So the use cases, as I discussed, it's about health monitoring, wearable health monitoring. So there are two specific use cases that we're working on. One is the monitoring of sudden cardiac arrest. Sudden cardiac arrest is something like a variation in the ECG pattern. If you might have seen this defibrillators all around the buildings. So if you have, if you can apply the defibrillation, apply the electric shock, or at least give CPR within like 3 to 4 minutes, there is a higher chances of survival in the case of sudden cardiac arrest. So within 3 to 4 minutes, if you don't apply CPR, the person will not have oxygen supply to the brain, the blood supply to the brain will be cut off, and the person dies basically. So one of the use cases that we look at is this monitoring for sudden cardiac arrest. And again, this is a huge problem. A lot of people, in fact, around 30% of all people die of cardiovascular diseases. And this is one of the main component of that CVD umbrella. And so the idea here is by using our proposed platform, you can detect the onset of sudden cardiac arrest early. You don't have to send the data to the cloud and wait for the cloud to analyze it and send it back. You're not affected by network latency or network outage or cellular, or even if your cell phone drains out. Those kinds of situations are taken care of. And another use case that we're looking at is the onset detection of cardiac arrhythmias. Cardiac arrhythmias is not there are different types of arrhythmias. Many of them are not a serious problem, for example, but they could lead to a serious problem. For example, something like atrial fibrillation, which you can use your smart watches like Apple smartwatch to detect these days. So the atrial fibrillation in itself is not a serious problem. It is a type of an arrhythmia, but it could lead to what we call like a stroke. So if your heart beats violently, and it could trigger particles going from your bloodstream to the brain, and it could block your blood vessels in the brain and cause a stroke. So we are also the second use case that we're looking at is the onset detection and classification of cardiac arrhythmias. Right, so that's a summary of our project. We just started the project, and we have some work going on. So the possible areas of collaboration, because there are 3 partners in this project, I'm just mentioning the possible areas of collaboration with myself. I'll be interested. So the AI hardware we are building can support different types of AI workloads, such as graph neural networks, transformer workloads, CNNs, RNNs, and it has this capability to dynamically vary the data path, which is currently not commonly available in commercial products. And we are also working on other areas of collaborations, could include model compression. So we have several work going on AI model compression for edge sensors and IoT and wearable sensing. And so I think this part we already discussed a bit. So for you colleagues who would like to collaborate with us, you can definitely, will be definitely interested in applying for the Horizon EU projects, ELANet, or the Marie Curie ITNs. So we are planning to coordinate one Marie Curie ITN next year. So if any of you are interested in this kind of work, you can ping me. For US colleagues, for Ireland and US have a specific R&D program. So if you can Google it and find the details of it. And each EU country may have some specific programs directly with the US. You can also look at that. And there are different staff-student exchange program in my university. I think almost every university will have. So this could be another opportunity for collaboration. That's it. Thank you.
And always is a challenge to have the presentation at the end of the meeting. So, but we have time for one short question for you. So it seems that the presentation was very clear. So then I thank you very much for the presentation. I thank to all of the presenters, and Cohen, the floor is yours now.
Yes, okay, thank you. So we are a little bit over time. I will keep this short. So now there was a bit of a discussion possibility to, well, if there's more questions, I don't know. Somebody would like to ask a question about this event. So I would like to thank, first of all, everybody for coming here and for doing the presentations. I learned a lot of new things. There's more than I was assuming, so it actually exceeded my expectations, which is very good. So this is very useful input for the kickoff that we will organize next week. So we know that this is a good model. We could duplicate this a couple of more times to find more members, because we have to build a community now between 70 and 100 people, almost equally split among the US and the US. So the instrument that the NSF will use in order to fund exchanges with Europe is what they call the DCL, the Dear Colleague letter. Apparently, it's new for me, but that's the instrument that will be used. So if you have interest in joining this effort here in this project, I think you should apply for membership. That means that we keep you informed about our progress, about the calls, the events that are being organized, the funding opportunities, etc. So you don't have to send me an email now. You will get an email from us, and you will also get an invitation there and some instructions on how to do that. But there's more than that. This is a small group. We picked some projects from NSF, we picked some projects for the EU, but there are many more activities going on in Europe and in the US. So if you, not only if you have interest, but if you know somebody who would fit this initiative very well, I would say, well, let us know. We can contact this person. Obviously, we are looking for people who are running a project, because then there's some kind of collaboration between projects in the US and in Europe. That would be very nice. But if you have good candidates, please let us know. We have a good network in Europe. Our network is much smaller in the US. So for the UX colleagues, if they have suggestions, feel free to to help us. There are a number of constraints, of course, requirements. So people have to be active in the computing continuum, distributed computing, swarm computing, and AI on the edge, etc. But we all know this. We saw examples of this today. And of course, they could join because they want to participate in the exchanges, but they could also join because they want to be involved in the effort, in the vision activities that we are going to do, the white paper that we will develop. So if there are people who show interest in contributing to this effort, and I learned from the NSF that even there could be funding for that, to attend a meeting to do that. So that would also be very welcome. Somebody who would like to organize an event, a networking event, is also very welcome to make suggestions to us. And also we have a summer school. If there would be people who show interest to teach in the summer school in this area, feel free to contact us, and we will see whether they fit in the concept that we have for the summer school. The summer school that we organize is mostly attended by European researchers and students. So I think for this project, it would be nice to have US teachers, because then we have some kind. It doesn't make sense, not much sense, to have a European teacher teaching the European students, because then we are not realizing the goals of this project, where we want to bring the two communities closer together. So these are a number of opportunities we could already work on. We will, I'm at this moment already collecting the slides of all the presentations, so we will share them with you. It will not be next week, because we are busy organizing a big conference next week, but later this month, you will definitely get more news from us and more instructions on how to join this effort. So this is my final word. I don't know, Rolf, you are the project officer. Maybe you want to add something, or Jan?
Not much to add. Thanks for all the people who took the time and your effort to the really stimulating and enthusiastic presentations. I think I also learned a lot. I think we definitely have to continue to work on these principles, understand these principles, to bring together the research and the applications. And I think there, you know, every project, every presentation had a different starting point, a different spirit. And I would like to emphasize, put emphasis on the fact that the joint collaboration is not limited to the projects which we are here today. It's on a bilateral basis, on partner basis. I think I learned something in the different areas where we could think of matchmaking between pilot actions, or what we call testing experimental facilities, which could have a relevance, and we have to see, you know, whether they have some free funds, and whether we could align it even at proposal stage if we have something coming up, in order to leverage that one, and not to reinvent the wheel, or to go faster. So I think both sides, European and US sides, thanks for your time. For the European ones, wish you a good weekend, And for the American ones, you know, I still have to finish the day and or shuffle your snow. All the best, stay healthy, and thanks again. Staying tuned.
Okay.
Thanks, Rolf. Thanks, Ko, and thank you very much to everybody.
Thank you all.
Thank you.
Bye.
Have a nice weekend.
Thank you. Goodbye.